welcome back to another Shift Remote. This is the 10th in our 12-part series of mini virtual conferences where we bring together the brightest developers online for you, our fantastic and incredible audience of virtual listeners. Now, many of you have been with us before. For those of you that haven't been here, welcome. My name is Bilal Harry Khan, and I'm going to be your host for this conference, which means that I'll be popping up every now and then to introduce the next in our incredible lineup of speakers. Now, we have a jam-packed program for you today, which is really exciting, which means that there's a lot to get through. So you might want to ask a few questions. We've got the chat there on the right. Open it up, say hello, let us know where you are in the world. And we've also got the Q&A that will be popping up as a chance for you to interact there should you have any questions. And our team on the back end will try and get those answered and through to our speakers for you. The hashtag for this event is #ShiftRemote. Take a photo, take a selfie, take a video and let us see where you are on social media, wherever that might be in the world, because we love it when you do that and stay interacted with us here at Shift. Logistical things though, this conference will be going for about 2.5 hours. At the hour-and-a-half mark roughly, we're going to take a 5-minute break, which is your chance just to pop out, grab yourselves a drink, and then be back here in front of the screen so you don't miss what we've got planned for you in our lineup. Now, before we get going, there are a few thank yous that I need to do, and it wouldn't be a conference without our sponsors. So a huge thank you once again to the team at Microsoft, Infobip, Raiffeisen Bank, Autodesk, Microblink, Barrage, Azure Idea, ICT, Japania, Venture, Pseudocode, 5, Ars Futura, 9 Dots, Infinuum, Q, Nanobit, Get by Bus, Aspira, Code Anywhere, and Pluggy. Without you, none of this would have been made possible. So thank you all so much once again. And thank you again to you, our listeners, for being here. Now, before we get this show on the road, I'd love to introduce you to the CEO and founder of Shift Conference and Shift Remote, Ivan Burazin.
Episode number 10, here we are, of the Shift Remote series. It is going to be a long one today, but there is a reason for that. This is the all-star episode. I mean, we have speakers from Amazon, Facebook, Google, Amazon. 2 of them are from Amazon. It is a blast. All the people from the serverless world are here to inform you with what's going on and what's happening. So please do enjoy. Also, after this event, there will be another pause until mid-December when we have our last 2 events of the Shift Remote series. So please subscribe if you have not now to keep up to date with these events. It has been a long ride, but it has been a joyful one. I hope you've enjoyed as much as we have, and see you soon. Enjoy.
Thank you so much, Ivan, and let's get ready for our conference. And if you're ready to go, let's get a smiley face there in the chat. That would be lovely. Now, our first speaker is a web and mobile developer, open source enthusiast, and author and speaker. We're really excited to bring to you a senior developer advocate at Amazon Web Services. We're talking about distillation off the cloud. Let's welcome Nader Darbit.
Hello everyone, welcome to my talk. Today I'm going to be talking about building Next.js apps on AWS. My name is Nader Darbit. I'm a senior developer advocate on the AWS mobile team, and by trade I'm a front-end developer focusing on web and mobile development, mainly React and React Native over the last few years. And over the last couple of years, 2 years, I've been working at AWS, and this has kind of been my first involvement in building scalable back-end solutions. So I kind of bring a front-end developer's perspective, I believe, to a lot of the stuff that I talk about. And I actually have a book that I've released recently that covers some of the stuff we're talking about today. So if this interests you, check it out. It's called Full Stack Serverless, and it's available from O'Reilly Publications. Now, this talk is going to be broken up into 2 main parts. We're going to be talking about the deployment process of Next and how you would do that with AWS. And then we're going to talk about the APIs that you're going to use to interact with different backend services. So with Next.js, you have this idea of calling APIs from the client or the server, or for even API routes. So we're going to be talking about how you can do that, and call authorized API requests in these different environments and things like that. So before we dive into dealing with Next.js on AWS, let's talk a little bit about Next.js itself. If you look on the internet, you might find this as a description of Next.js. a web framework built with React, but there's a lot more that goes into it, and you've probably heard a lot about Next.js. So let's talk about what makes Next special. Well, when you think about React and you think about using something like Create React App, you typically are going to be given a single page application, and this is going to be a client rendered app, meaning that everything that you do is going to be kind of bundled in this single JavaScript bundle, and then you're going to be serving that even when you're routing to and from different pages. All of that is done in the client. What Next.js brings to the table is this idea of combining client-side routing and client-side rendering when necessary with pre-rendering of HTML. And you can do so writing React. And there's a couple of different ways that you can do this. One is using server-side rendering. When you make a request to your endpoint or to your page, the page is then generated dynamically on that request and then pre-rendered, and the HTML is sent as a response. There's also the idea of static site generation or static page generation, meaning that there's a build step, and then during that build step, the HTML is created and then given to you as part of the build. And then finally, what's been added somewhat recently is this idea of incremental static generation, meaning that you generate your site using a statically generated build, and then you might dynamically have additional endpoints that need to be served. And if they haven't been part of that initial build, Next.js will incrementally build that static page and serve it from a cache after it's been built. So why does pre-rendering HTML matter, and why are people interested in this stuff? There are a few benefits to pre-rendering HTML. The first is speed and performance. So if you've statically generated a page, you can then serve that page via CDN from some edge location, and it can be cached. When a user then requests that page, it will be served from the nearest edge location that user is close to, and then the user is going to have a very good user experience because the page is going to load very, very quickly. The other is search engine optimization. When you're working with a single page application, you often have a really hard time getting good SEO. With a pre-rendered page, it just works really well out of the box because you're serving the browser exactly what it's expecting as far as metadata is concerned. Any HTML can be completely customized, and the crawlers will find your page a lot easier than a single page application. Also, pre-rendered HTML is a lot more resilient, scalable, and secure because there's a lot less things happening at runtime. All of this stuff is typically going to be happening either in the build process or it's going to be happening in that pre-rendering phase. And then when you're served your static HTML, there's just a lot less entry points for someone to take advantage of your app. Now, pre-rendering can be done in a couple of different ways. So with static generation, this is typically done in a build step. And once you've had this static build, it can be served via the edge via some CDN. And if you have any data, any dynamic data, your data is going to be prefetched during this build phase. And you're typically not going to be working with any type of authenticated or authorized data. This is typically going to be public data. So a lot of times when you think of a statically generated site that works really well, it would typically be something like a blog or maybe an e-commerce site. Now, the other way is going to be SSR or server rendered. And with a server rendered page that is pre-rendered, it's going to be served on demand when the user requests that route on every single request. And typically for this to work, you need to have some type of runtime execution, either a server or a serverless function. A lot of times what you're seeing people do now for the serverless stuff is going to be a serverless function. So the question is, which one and how do you choose which one? Well, if you look at the documentation for Next.js, they recommend using static generation when possible. So this is kind of a snippet out of their docs. We recommend static generation over server-side rendering for performance reasons. Static generation or statically generated pages can be cached by CDN with no extra configuration to boost performance. However, in some cases, server-side rendering might be the only option. Now, that comes the next question. How do you as a developer kind of choose between the two? Well, Next.js basically makes this pretty easy for us because by default, it's going to statically generate any page that's been created in your app unless you export get server-side props or unless you've bought into incremental static generation. Now, in the static generation phase, you can do things though with your data fetching by exporting other functions. The first of those being get static props. So with get static props, this function will fire during the build phase, and you can then call your API to get whatever type of data that you need at build time. You can also buy into incremental static generation by setting the fallback flag to true. There's also get static paths, which is also something that's part of the static generation phase. And this goes along with get static props for generating pages at build time. So you might think of something like a blog where you have n number of pages. During the build, you're going to get maybe an array of 15 pages. And then in get static paths, you can generate a new page in your Next app for each of those posts, and then pass whatever props that you would need into get static props. So that page would then be able to access that data via props. To buy into SSR support, you can export the get server-side props function, and whatever data is returned from this function as props will be available in the page as props. And then finally, for API routes, all of these are going to be server generated or server rendered. Now, Next ships with a couple of different scripts out of the box. You have your dev script, and then for your actual build, you have Next build, and then to test out a build, you have start. And then there's another script that you can run if you'd like to kind of buy into only the static generation phase, and that is Next export. So this is only going to work for statically generated pages. You can fetch data, build time, and all of that, but you're not going to be able to do stuff with SSR support or for API routes. When you run a build, Next gives you this nice CLI output to kind of give you an idea of which pages are doing what. So, for example, you can see that the root page here is a statically generated page. The server rendered page is the /about page. And a statically generated page that uses get static props is /contact. So for all of your pages, you get kind of this nice overview of what is going on. Now that we understand how Next.js works, let's now look at how to deploy Next.js on AWS. The method that we're going to be taking a look at today is using the serverless framework. The serverless framework has a really nice component called the Next.js serverless component, and this is kind of a really easy way to deploy Next on AWS. And using this, you get all the stuff that you would expect from a Next site. You have SSR support, API routes, static site generation, and even incremental static generation. And all of your SSR and API routes are served via Lambda at Edge, and all of the client assets are served from CloudFront. So what you basically have is a single deployment, and then this deployment will be replicated across a bunch of different places and then served to the user from the nearest edge location. So to understand a little bit more about how CloudFront and Lambda at Edge work, let's take a closer look. CloudFront is an AWS service that is a global CDN, and from this CDN you can serve static content such as videos, images, and HTML, but you can also serve dynamic applications, APIs, things like that. And this is a massively scalable service. You actually see a lot of other services that are in the Jamstack and serverless space built using CloudFront. And at the moment, there are over 200 edge locations, and this number continues to grow. And then the next service is Lambda at Edge. And Lambda at Edge is an extension of AWS Lambda that essentially allows you to run your functions at these edge locations globally. And then once you deploy a single Lambda function, it's replicated across all of these different edge locations. And then your function is triggered in response to an event that is managed by Amazon CloudFront, the CDN we talked about just a moment ago. So with Lambda at Edge, you basically would pick a region, typically the region closest to you as a developer. You'll deploy your function into that region, and then automatically Lambda at Edge will replicate it across all of these over 200 edge locations. And then when the user requests that site or that function, it's going to be served to them based on their current location, making it very performant. Now, to deploy using the serverless framework, it's pretty simple. You just create a serverless.yaml file at the root of your Next app, and then you specify the component as the SLS next/serverless-component with the most recent version. I will probably recommend 1.17.0 at this point in time. That's kind of the most recent version. And then once you've created this file, all you have to do is run npx serverless, and your app is going to be deployed. And we're going to actually walk through a live demo of how this works in just a moment. You can also set up custom domain names pretty easily. So if you have a domain name you'd like to use, you go into AWS console and you add it into Route 53, and then you can set it as the domain in your serverless.yaml file right below where you've specified the component. And you run the deployment again, and everything should be ready to go. You can also set up cache policies. So for instance, you might want to have a certain cache policy as the default and then set different cache policies for different routes. You can do that setting things like your minimum and maximum time to live as well as a default time to live. Finally, you can set caching policy for your public and static directories. So for instance, your images and things like that, you have control over the caching policy there as well. Now that's kind of the deployment process. Next, let's look at the API interactions. So how are you going to do things like authorization, authentication, and data fetching in the next step on AWS? One of the things that my team has really been working hard on is to create a unified data layer across client serverless, SSR, and SSG apps and sites. So essentially, we want to have a client library that works on the front end and services that kind of interact with these client libraries on the back end that work across all of these modern web stacks. So one of the things that we've created and launched recently is SSR support for the Amplify libraries. And to do the enablement, all you have to do is set an SSR flag to true in your Amplify app. And this is automatically, once you've maybe upgraded to the newest version of Amplify client libraries, this is automatically going to flip the switch to make SSR true, and then your app is going to be SSR compatible. And then what you can then do is you can start interacting with some of the APIs that Amplify provides. The main ones being authentication, data store for accessing data, and API for accessing data. And when you think of API interactions and why you would need SSR support, most of them kind of revolve around auth and data. So when you think about data and you are maybe working already with Amplify and a client rendered app, you might import the API category from AWS Amplify, and then you might make some type of GraphQL API call passing in a query, and then you would have like some data that's returned from you. So this still works for a statically generated build phase, so you don't really have to worry about anything. That automatically just works now. But what you might consider is, what about if you're making an authenticated or authorized request in an SSR route or in an API route? You can now actually get that user session and have that as built into the headers for you by using the with SSR context utility from AWS Amplify. And then you would just import this new utility. And instead of importing API directly from Amplify, you would destructure the API category off of with SSR context, passing in the context that gets passed in either to the function or the API route. And then this API category will allow you to then make API calls with all of the proper authorization headers configured if there is a signed-in user without you having to write any extra code. The same thing goes for auth. So for instance, you typically would just import auth from AWS Amplify in a client rendered page. And a server rendered page or an API route now, if you want to use auth, you would import the with SSR context utility from AWS Amplify. You would then destructure auth off of with SSR context, passing in the context. And if there is a signed in user, you will now have access to that user and their credentials based on the session that was retrieved out of the context. So let's take a look at a couple of examples and then we'll do a live demo. Here in an API route, we want to know if the user requesting this API route is authenticated. So what we're going to do is we're going to destructure the with SSR context utility from Amplify. We're going to then pass in the request to with SSR context, and this is going to give us the auth class as a return value. What we can then do is call auth.currentAuthenticated_user from the API route. And if there is a user, we can do stuff with that. So that's kind of a really simple way of kind of working with the current authenticated user or the current, user session of whoever is or not signed in. But really one of the most interesting things in my opinion is the combination of auth and data. So for instance, You might be using some type of Amplify backend or not. You might be using your own backend, but either way, you need to know that current authenticated user. So using the last method that we looked at just a moment ago, you can kind of handle that yourself. But if you're using the Amplify client libraries, this is actually handled for you. And you can do this, of course, in either getServerless.props or API routes. So for instance, let's say we have an API that is protected, and it's going to need to know that the user is currently signed in order to authorize that request. And if it's not, we want to kind of return unauthorized. So to make this work, we'll import with SSR context from Amplify. We'll destructure the API route. We'll destructure the API category out of getServerless.props by using this new with SSR context utility. And then we have this API that we can use, and it will be aware of the current user session. So in this authorized request, we don't have to pass anything here. We just call api.graphql, and the API library automatically is going to send the proper authorization headers, the identity of the user along with the request, if there is a user. And if there is not, it will catch, of course, and throw an error. But if there is, the data will be returned, and we can successfully use that data. So I think this is interesting, but really to kind of get this idea across, let's take a look at a demo. And what we're going to do is we're going to take a couple of different routes that are currently not using the SSR support, and we're going to enable it and see the difference. And then we're going to deploy this using the serverless framework. So what I'm going to do is go ahead and close this. I'm going to go ahead and run this app. And what we're going to do is open this up in a tab here. And then finally, we're going to go ahead and open this also up in a text editor. All right, so we have a pretty basic Next app here. We have a profile page. We have a protected SSR route. And then we have a protected client route. What I'd like to do is, in the profile, I'm going to go ahead and create a new account. I will use my MFA code to authenticate. And then once I'm confirmed, I'm going to go ahead and test out a couple of these routes. So I can go to the protected SSR route. And what I'm going to see is that I'm actually redirected to profile because it's basically not recognizing that I'm authenticated. If I go to the protected client route, this should work because the client support hasn't really changed. And then I'm also going to go to this API route of check user, and it's going to say user is null because I'm currently not using the proper mechanisms for SSR support. So what we're going to do is we're going to kind of change the API route, and we're going to also change the protected SSR route. So I'll go ahead and open up, first of all, the protected SSR route. And maybe instead of redirecting, what we're going to do is maybe return some props of authenticated, false, instead of redirecting. Okay, so basically what we have going on here is we're importing the auth class from Amplify. We have this component that if they are not authenticated, we say not authenticated. And if they are authenticated, we say hello from SSR route using their username that's passed in as props. And then in getServerless.props, we're basically calling auth.currentAuthenticated_user. If there is a user, we're going to log that user out, and then we're going to return authenticated true and their username. And if they're not signed in, we're going to return authenticated false. So if I save that and I go back to protected SSR route, we see not authenticated. So let's go ahead and change that. So instead of importing auth from Amplify, we're going to import with SSR context. And then what we're going to say here is const auth is equal to with SSR context, passing in the request. And now we're basically using the SSR aware component that is now going to be aware of the current user session that's passed in via the request. So if I save that and I refresh, then we see that the route is now recognizing that we are signed in. So we now have the current user session available in the SSR route, and we can do whatever we'd like with it. We can call another API, we can do some type of logic, we can do whatever we'd like. The next thing we're going to do is kind of take that idea and move it into the API route as well. So this API route basically is also using auth from Amplify instead of with SSR context. So what I'm going to do is I'm going to say const auth is equal to with SSR context. Passing in the requests. And then we're calling auth.current authenticated user and everything the same exact way. So if I refresh and I go to API/check user, then we see that the user is returned and we have kind of all of the user's metadata. The next thing we want to do is deploy this thing using the serverless framework. So what we're going to do is create a new file called serverless.yaml. And in this file, we're going to go ahead and say my new next app. And then we're going to specify a component. And this is going to be at SLS next. And then it's going to say at /serverless component. At 1.17.0. And then what we can do now is deploy this by running npx serverless. And this is going to now go ahead and deploy our next app to AWS and kind of take care of everything that we would need. And this takes a couple of seconds to kind of deploy on the first time. So usually around 45, 50 seconds for the first deployment. And then for some deployments that happen after that, it's not that long, maybe another 10 seconds or something like that. But what we should be able to do once this deployment is successful is test out our API routes. We should be able to test out our server-side routes. All of that stuff should kind of work fine. So once the deployment is successful, you should be given your bucket name, the distribution ID, as well as the app URL. And then when you run another deployment, you'll just run npx serverless and your app URL will stay the same and you should be able to kind of test it out. So what we're going to do is we're going to go ahead and try this out. So we're at the live app now. Might want to zoom in a little bit. What we should be able to do is still sign in. And we should be able to still access our server-side routes as well as our API route. Oops, it looks like for some reason our API route is, I think I know the problem. I think in an API route, you need to also configure Amplify again. So basically, if we go to app.js, we have this going on here. For the API routes, you need to reconfigure the SSR flag to true. So it would look something like this. We would go up maybe one more directory. So basically, yeah, if you're using this with API routes, make sure you reconfigure Amplify. And that's really about it. So let me go ahead and pull up my slides to finish this out. I encourage you to give this a try. Working with Next.js with Amplify, pretty nice experience if you're looking for something that combines data, auth, you need hosting and all of the different things like image and file storage and stuff like that. And if you'd like to learn more, check out our Discord. and go to docs.amplify.aws to learn more. And then I've also created a blog post that is 2 parts that goes into a lot of this stuff. Check out the complete guide to Next.js authentication, and then attached to this article is a part 2 that goes into the data story. And my team is really happy with where we're at, but we also look at everything like we're still on our first day, like we have a long way to go. So we've done a lot, but we still have a lot of plans for things that we're going to be doing in the future. So stay tuned. And if you're interested in this stuff, check me out. Follow me on Twitter, Dabbit3, or follow AWS Amplify on Twitter. So thank you so much for checking out my talk. I hope you enjoy the rest of the event. Thank you for having me.
Thank you, Nada. And with that, we're moving into our next speaker, and we're talking about building resilient serverless systems. We have a senior technology leader with more than 20 years of experience managing the development of both complex web and mobile apps for both domestic and international businesses. They spent their early career running a web development agency, working with over 200 companies. They've been the lead architect and developer for hundreds of websites, including several e-commerce platforms, custom CRMs, and the F7 platforms. They worked with big data and complex analytic systems running on leading cloud edge infrastructures. Let's welcome Jeremy Daly.
Hi everyone, I'm Jeremy Daly. Thank you so much for having me at ShiftConf. This is really exciting to be here and I really appreciate it. So today we're going to talk about building resilient serverless systems with non-serverless components. We've got a lot to get to, so let's jump right in. So again, my name is Jeremy Daly. I am an independent consultant working with companies building in the cloud. I have been doing this for a very, very long time, which is why I have all this gray in my beard. I started working with AWS in early 2009, and then once Lambda came out and became GA in 2015, I moved into the serverless space. I blog at jeremydaly.com. I am a contributor to a number of open source projects. I also do some speaking. I publish a weekly newsletter all about serverless and everything that's happening in the industry, Off by None. You can check that out. And I also host the Serverless Chats podcast, as well as a new series that will be launching soon called the Serverless Spotlight web series. I am an AWS Serverless Hero, which is a great program that allows me to get some sort of early feedback into the products that they're working on and help contribute to the serverless space and the direction of that, which is a fabulous program, and I really love being a member of this because of all the great people that are part of this program. Okay, so today's agenda is kind of packed, so we're going to go through this quickly. We're going to talk about what is resiliency and what is serverless. We're going to talk about working with less than scalable relational database management systems, using unreliable APIs, managing API quotas, and decoupling our services. And then finally, we'll get into other non-serverless components and how we deal with that. So we need to talk about what resiliency is first. So resiliency is the ability of a software solution to handle a problem, to provide an acceptable level of service, even if something is broken. So this is not about reliability. It's about being able to, so it's not about being able to prevent failure. It's about being able to understand ways in which your system can gracefully deal with it. And this is important because with distributed systems, everything can't always stay up. So we need to figure out how we can keep as much of our system running as possible when we have a problem. All right, so let's just get into what serverless is. Now, again, I know this is not a serverless conference, but I think many people have heard these things such as no server management, or maybe they heard flexible scaling, this idea of paying for value or only paying for use, and then also this idea of automated high availability. Now, these are all really, really key tenets to the serverless, serverless technologies and what we're trying to do with serverless. But another important thing to remember is that there are a lot of configuration that are required and knowledge of the cloud services you're using. Even though we're reducing the amount of ops we may need to do for certain services, we now need to understand how those services work, at least so that we can interact with them. And the other thing is that serverless is highly event driven. That means that we're going to be receiving events and reacting to events. It's not a very synchronous model. So this is something we'll get into a little bit about how we can use that to our advantage to build these highly resilient systems. Today, we're going to mostly be focusing on the flexible scaling aspect of that, just because serverless is so scalable that often we have to deal with other systems that aren't scalable. So again, we'll talk about that. All right, so I'm going to talk mostly about systems and services in the AWS ecosystem. So AWS is I think far more advanced with a lot of the other services that they offer. Many clouds are catching up. But the way that AWS thinks about it is that there are a couple different buckets. One is the serverless bucket. Now, these are services like Lambda and DynamoDB and EventBridge and AppSync, things that essentially you don't have to worry about provisioning. You just basically have to say, all right, I want to use this service, and it's essentially going to scale as much as you throw at it, it's going to scale to handle that. There's another category that is managed. Now, these are things that you don't have to worry about installing patches or managing the underlying servers or things like that, but you do have to think about the provisioning, provisioning these things and make sure you have enough capacity for your application. And then finally, there are these things that are not serverless, okay? So this is anything that might run on a VM, such as EC2s in AWS, or anything that you have to install and manage yourself on those VMs, things like Kafka or Cassandra or even Kubernetes and things like that. So these things are definitely not serverless. So it's important that we understand the difference between these three different things, because everything is going to affect how other systems scale and how other systems can support increases in traffic. So everything has limits. So this is an important thing to think about. Even when you're dealing with serverless components, you have things like reserved concurrency, which only so many concurrent users can attach to a specific Lambda function. You have function timeouts, right? Lambda can only run for 15 minutes. You have memory limits of just over 3 gigs, where that limits how much processing you might be able to do in a single Lambda function. And you have network throughput, right? You can only transfer data between two components as fast as the network will let you, and that is also dependent on whether or not there's other heavy network traffic going on. So some of the components that we're going to talk about are better than others at handling scale and sort of not worrying too much about those limits. But as long as you know your limits, then that's a good way to go ahead and approach the architecture of a new application that you might be building or re-architecting one. So let's look at a simple web service. So if we are building a simple serverless web service, we might say we're going to have our client connect to an API gateway that connects to a Lambda function that queries the DynamoDB, and that information is sent back to the client. Now, in this situation, it's great because API gateway will scale almost infinitely. Lambda, depending on your settings, will scale almost infinitely. And DynamoDB is highly scalable, and you can very easily make it so that DynamoDB can handle an incredible amount of load, whether that's with caching or some other techniques. But if you remember that the song from Dire Straits from the early 80s, I think it was I want my SQL. And that's a problem in that many developers still want to be able to use relational database management systems in order to build their serverless applications. So if we look at our simple web service or simple serverless web service again, and we replace DynamoDB with RDS, which is the AWS relational database system that lets you do that lets you do MySQL or Maria or Postgres, the problem is that this is not that scalable. Now, some people will argue saying, well, you can have really big clusters. That's true, but from a standpoint of over provisioning and scale and flexible scaling, RDS just doesn't necessarily do this for you. So now we have the simple not so serverless web service. And of course, the problem with this is that we're gonna be limited in terms of how much traffic we can get if our RDS system and our database is the bottleneck that's going to limit that traffic. So there's a couple of reasons for this, because relational database management systems and functions as a service don't really play nicely together. Now, this has a lot to do with the concurrency model. Every concurrent invocation of a Lambda function requires a separate connection, so there is no such thing as connection pooling directly from a Lambda function. Also, there's a limited number of DB connections that are going to be available from your database. Even if you keep making it bigger and bigger, at some point you're going to hit that limit. And then finally, because of the way that Lambda functions work, when they recycle themselves, meaning they go away and they basically free up that capacity again, they don't always close the connection to the database, which sometimes leaves these zombies. So there are a number of different ways that we can manage database connections to our database from Lambda functions or from functions as a service. We can increase our max connection setting, right? But the problem with this is that we then are likely going to spike our CPU on our database, and that's not a great way to do it. We could limit the concurrent executions, but this is something that might make your customers mad if they can't access the data. because you're throttling them in some way. You could lower your connection timeouts, right, which is sort of a cross your finger strategy. Let's hope that that these recycled zombie connections, these zombie connections go away automatically for us. You could limit connections per username. These are things, these are sort of games that you can play to try to, depending on which part of your application is connecting, it has more capabilities or more connections into the system. And then finally, you could try closing connections before a function ends, which I've seen recommended a number of times. This is absolutely a terrible idea because it takes so much overhead and so much CPU to actually establish that connection originally. You want to try to maintain connections and reuse connections as much as possible. So all of these are really not good ways in which we want to try to connect to databases. So what are some better ways that we could do this? So we could implement a good caching strategy. We're going to get into each one of these individually and go through it. And this is sort of, scalability 101, good caching strategies, but we'll talk about it more. You could buffer your events. If you are doing something that is a heavy write application, you can buffer events for throttling and durability. And like I said, we'll talk about that. You can utilize a proxy service, or you could manage connections yourself, right? So these are better ways, and let's look at each one of these and figure out how we can implement these in our serverless applications so that we can add that resiliency to make sure that these downstream systems don't become a problem for us. All right, so implementing a good caching strategy. So this is pretty straightforward. Basically, we have our client API gateway, calls a Lambda function, and now we want to get some data from an RDS. So this is when we have a heavy read application, right? Maybe it's news stories, maybe it's blog posts, maybe it's comments, something like that, where we're reading a lot of information from the database. So rather than connect to the RDS cluster directly from our Lambda function, the first thing we would want to do is actually check Elasticache. Elasticache is a service that just does Redis or Memcache in AWS, but essentially we want to check that cache for whatever value or whatever record we're trying to get. If we get a hit, great, we can respond back to client. We never even need to touch the database. But let's say we make a request and this time we get a miss. Well, then what we have to do is we have to then reach out to our database. We need to grab the data that we have. And then because Elasticache is not a write-through cache, it's not going to automatically update or add it to the cache for us. We do need to manage this ourselves through the Lambda function. But once we do that, we can go ahead and respond back to the client and everything is good to go. So a couple key points here is that we only want to create new connections to the database when there's a miss, all right? So there's a possibility that once that cache gets nice and warm, that you don't need to connect to the database very often. And if you don't need to do that, then you limit the number of concurrent executions that need to maintain that relational or that connection to the database. So again, not always perfect, but it's a good strategy just to keep those connections down if possible. Again, we're dealing with caches, so we want to make sure those TTLs, the time to lives, are set relatively low, or at least appropriately so that the data isn't going to get stale. And if you do have some other application that's writing and updating those values, you want to make sure that you're interacting with that cache as well and clearing that out. Now, if you've taken Computer Science 101, you probably know that you shouldn't be using a cache to prop up a weakness of a database, that you should rely on the database, or the database should be sized appropriately, and that the cache is more of an efficiency thing. In this case, it's both, right? So we are using it for efficiency, but I do get what you're saying, and yes, you still need to size your database cluster appropriately. If you expect 1,000 concurrent users and you need 1,000, you need 1,000 connections, then you should size your database to handle that. But you're putting that cache in front of there not only to hopefully mitigate the number of connections you need, but also just as some resiliency, right? So if that database goes down, if you can still serve up 80% of your traffic because you have that in a cache, that's a good way to handle that. All right, so the other thing we need to think about is when we're writing data, when we're doing sort of write-heavy applications, maybe things like a webhook or something like that, do we need to know that it made it to the database immediately? And that may sound a little bit strange, but there's two different types of communication. Synchronous communication, which we are all very familiar with. That's when we make a call to a database, the database does something, it gives us the data back, and then we can respond back to our client. But the problem is that these are blocking requests, and that means that that database has to be available in order for us to make that connection. And the problem with that is that if you have something that's coming in very quickly, you don't want to lose those events. You don't want to lose the data that's coming in. And if your database is down, which it very well could be, especially if you get overwhelmed by, say, some sort of large, maybe you send out a huge email or something like that, and you're getting all these open webhooks and click webhooks and things like that coming through, you don't want to lose that. So there's another type of communication that is called asynchronous communication. And this essentially is a non-blocking request where rather than us trying to do something right away, we actually can queue it. And there's a lot of lightweight queuing mechanisms out there that allow us to do this. And that allows us to basically say, look, we've captured the event, but we don't immediately need to hit that third party or that downstream system that could potentially be suffering from an outage or something like that. So if we think about how we would do this in a serverless application, you have a client, right? And maybe that's a webhook endpoint for your API gateway that calls a Lambda function. And now we want to get this into a relational database system. We want to get it into MySQL or Postgres or whatever. Rather than us sending it directly to RDS, we would put what's called an SQS queue, which is again, a very lightweight queuing system that AWS has, that allows you to actually do what's sort of like an asynchronous request. We send it to the queue and we say, hey, did you get this message? If the queue says, yes, I did, it replies back to the Lambda function. And now we can reply back and say, hey, we got the message. Now we can't confirm that it made it into the database at this point, but we can say that we've captured that message. And now that message is durable. And even if our RDS cluster is down, we still have a copy of that message. So then the next step is we put another Lambda function here that's going to process the data off of that SQS queue. Now we can limit the concurrency here to match whatever the throughput is to that downstream system. And so we can say, look, we only want to do 50 at a time, right? And that's a good way to manage the number of connections that are needed because you can significantly reduce how many you process. Now, again, it might back things up a little bit, but eventually if it's enough to work its way through that queue, you're in good shape. So what we would do here is have this Lambda function attached to the queue. It would query it. This is synchronous, meaning that the Lambda function won't take it out of the queue until it's successfully processed. So now we can call the database, write that data there, get a response back and say, okay, hey, if everything went great, perfect, we tell the queue we got the message, we take it out of the queue, now we've got that hardened in our database. But if for some reason there's a failure, right, rather than us say, okay, well, like we're going to lose the message, we don't want to retry the same message over and over and over and over again. That's this idea of a poison pill, right? So instead what we do is we can write that message automatically, all built into the way that these systems work, into what's called a DL queue or a dead letter queue. And that allows us to take that message and store it for later so we can look at it later. So some really cool things here is that SQS adds an incredible amount of durability. It's super lightweight, it's highly reliable. Even if you have a really powerful database, there's always something that can go wrong there. The likelihood of SQS going down is very, very, very low because there's so much redundancy and resiliency built into that. So the other thing is that those throttled lambdas reduce that downstream pressure. So that doesn't matter if it's a database, it doesn't matter if it's an API, whatever it is that the likelihood of your downstream system being as scalable as something that is serverless on the front end is likely not going to happen. So it is possible, but if you have the ability to minimize the amount of traffic you send, then you can reduce that pressure and hopefully not overwhelm that downstream system. And finally, as we talked about with those DLQs, those failed events are stored, so you can go back and look at them later, and you might say, okay, that failed because it was a bad message, but it also maybe failed because your database was down. And if the database was down, then at a later time, you can replay it once that database comes back up. Now, this is not a serverless conference, but there are a bunch of really cool things you can do in AWS. Like, for example, you don't actually need a Lambda function to process this here. You can just use the API gateway, what's called a service integration, and you can actually just send the API gateway directly, the message directly from API gateway into the SQS queue, and then use that Lambda function later on down the process to actually do any validation of data and things like that. All right, so there's another option here. We could utilize a proxy service, all right? And this is essentially when you put something in between your Lambda function and your database so that your proxy service handles all of those multiple connections and maintains that connection pool for you. So there's things like PG bouncers, there's something called SQL Relay. The problem with any of these things is that you have to install them on some server. Essentially, you need a Linux server or something like that in order to host these. And so if you put this into the mix of an API gateway with a Lambda function calling an EC2 instance that then calls an RDS or calling a VM that calls a database, the problem is that in a serverless application, this is really not that serverless. So at least we could do is maybe put Fargate or something like that, which is a managed container service, serverless container service, if you will, that AWS has. And then finally, we have Amazon RDS Proxy. Now, this is something that's really, really interesting. It's a really cool service that came out. The question, though, is it a silver bullet? Well, it does some cool things. First of all, it will pool and share database connections. So it doesn't matter if you have 2,000, 3,000 Lambda functions calling this, it can go ahead and manage the connection pool for you on the back end and make sure that you're only using 100 or 200 or 500 connections to the database. So that's pretty cool. The other thing is that it automatically reroutes your failures. So let's say you have a primary and a backup cluster. If that primary goes down, it'll reroute it to the backup, and it will do that automatically without changing any connection settings or anything like that in your Lambda function, which gives you a huge reduction in time for failover. You can also use IAM credentials. If you're familiar with IAM, it's the security policies that we use on AWS. You can actually use those to control access to the database. You don't have to worry about storing passwords and usernames for within your application itself, which is pretty cool. And there's also this really cool thing, this connection pool maximum connection, so you could actually have it multiple pools accessing a single database, and you can restrict how many connections each pool gets based on the application and so forth. But it only works with Amazon RDS, right? And you still need to do capacity planning. So it does help dramatically. It is not a silver bullet, and it doesn't work with Amazon Aurora Serverless, for example. There's a couple of other things it doesn't work with, and the other thing is it adds cost, right? So again, if it's worth it to you and it makes sense and this fits into your application, then that's something you should do. All right, so the other thing we can do is manage connections ourselves. So I'm going to go through this quickly because, again, I'm not really interested in you necessarily using the service I'm about to tell you about, but I did want to kind of tell you just that there is a strategy you could use to manage connections yourself. So you could count open connections, close connections if the ratio exceeded some threshold. You'd have to check on sleeping connections and close those if they had high values, and then also retry connections with some sort of exponential backoff if you tried to connect and you couldn't. Now again, you'd have to be crazy to build something like this yourself, so I'm not suggesting you do it, but I did build something like this called Serverless MySQL. Again, not suggesting that you use it, just want to explain to you how it works and why this is a bunch of extra overhead that you need to do if you're managing connections from a fast to a relational database system. So in this particular case, we count open connections. We can just use the process list to do this. We want to close connections if the number of open connections and the connections that are being used exceed some sort of threshold for us. You can calculate your timeout, so you can say every 5 minutes, if it's over 2 minutes or something like that, I want to kill those connections. You can assume those are zombies. If there aren't any zombies, meaning that there's just no more connections available, but there's no zombies to terminate, then you just close your own connection. And otherwise, you can just try to kill any zombies just as a cleanup methodology or as a method. Again, close these, query that process list for the zombies, kill any of those zombies that are over that threshold, and things like that. And then in terms of reconnecting, if there is an error trying to connect, most systems will just fail and say sorry. What we want to do here is try to reconnect with something like jitter, which is just an exponential backoff algorithm that gives you the ability to do it in jittery, I guess, in which you're not doing 2 milliseconds, 4 milliseconds, 8 milliseconds, 16 milliseconds, because if a bunch of those pile up, they're all going to be retrying at the same time. So you spread those connections out a little bit. So the question is if you manage connections yourself, does it really work? It does. I've run a number of experiments with Aurora Serverless as the database engine with just 2 ACUs, which means only about 90 connections available. A gig of RAM on the Lambda function itself simulated 500 users per second for 1 minute. The average response time was 41 milliseconds with 0 errors. So again, not suggesting that you go out and use this or that you necessarily build it yourself, but if you are experiencing problems and you need to work with the system and RDS proxy doesn't work for you, then this is a viable solution. A lot of people are using this and some form of it in order to manage their connections. So the big thing, though, is that we shouldn't have to do this, right? And at least in the AWS ecosystem, they are building out a number of services that let us, mitigate these issues. So obviously we have this thing, or I shouldn't say obviously, but there is a thing called Amazon Aurora Serverless, which is great. It automatically scales for you. It's not quite as redundant as it could be in terms of failover and some of those things. It does take a little bit of time for it to move if one of the databases does go down, but it does save your data, 6-way replication, things like that. Very cool. Doesn't solve the max connections issue. The other thing we have is this thing called the Aurora Serverless Data API. So if you are using Aurora Serverless and you don't want to connect through your traditional MySQL or Postgres connection methods, then you can use the Data API. This is an HTTP API that allows you to connect. I love this service. I absolutely love it, but the throughput is a little bit slower, and I'm not convinced yet it's ready for synchronous workloads, although I do use it for a couple of synchronous workloads. It's nice because you can avoid VPCs when you're connecting to this database, or when connecting to your database. And then we talked about Amazon RDS Proxy. Again, it's added cost, doesn't necessarily address the auto-scaling piece of it, but there's a lot of different things you can do in there that you could potentially get Amazon RDS Proxy to be a really good process for you, or a really good system for you. All right, so let's talk about third-party APIs. So if you want to manage calls to a third-party API, you're calling Gmail, the Gmail API, you're calling Twilio API, something like that, we can implement a lot of the same things that we talked about for the database. So good caching strategy if we're doing something heavy read. If we're doing something heavy write, collect that with an SQS queue and process that against the API at a later time. And the other thing we can do is implement circuit breakers. So the circuit breaker is a really, really cool pattern for resilient applications and redundant applications, in the sense that what this does is this allows us to say, look, if we want to connect to the Stripe API, under normal circumstances, let's just say our Lambda function or whatever we're using for our compute connects to the Stripe API. It does what it needs to do. It responds back to us. We get back to the client, and that client can be anything from another SQS queue or some other system that it's processing off of. It doesn't necessarily have to be a synchronous API gateway call. But the idea here is that this is the happy path, right? The likelihood of this happening every single time is very, very, very low, because distributed systems are prone to failure because of all kinds of reasons. And what Werner Vogels, the CTO of Amazon, says is that everything fails all the time. And this is just something that you should embrace as part of a distributed system, being a distributed system architect and building these applications. Things are going to fail. So we have to think about ways in which we can mitigate this failure and have some level of resiliency and redundancy in here so that we don't lose events, and that we can make sure that these events get processed correctly. So what we do is, rather than call the Stripe API directly, we're going to put a status check in. And we could use a cache for this, maybe DynamoDB or even Elasticache, depending on whether or not you're in a VPC or not. And what we do is we check and say, is this circuit currently closed? Which means if it's closed, electricity can flow through, which means we can send our messages through, right? So we call the Stripe API. If the Stripe API responds correctly, great. We just reply back to the client or tell this SQS queue, yep, we got it, everything was processed, great. But if it fails, what we want to do is we actually want to increment a failure count, right, and calculate some sort of threshold so that we know that if we go over a certain amount of failures, we want to eventually fail. So we can reply back to the client and say, look, we can't process this message right now. And if we do this a couple of times, eventually what happens is we want to open that circuit. So the message comes through, we say, oh, no, the Stripe API is not responding to us right now. It's open, so we can reply back to the client immediately and say we can't get to that. Now, of course, we can't wait indefinitely. We have to test it every once in a while. So that's when we do what's called a half-open request. So we check to see if the Stripe API works. If it doesn't, no problem. We just continue to not send traffic. But periodically, we keep checking, and eventually, hopefully, we get a successful call. And so now we can tell the system, hey, the status has been closed, and all the data can continue to flow through here. So this is a very, very good way to manage and be sort of a good net citizen or netizen or whatever you want to call it, because the last thing you want to do is overwhelm a struggling API with more calls. So a couple things here is cache your cache with warm functions. If you're calling DynamoDB or Elasticache every time, that might get some heavy communications, and you might have some hotkeys and things like that. So you want to be careful. You can actually cache some of that information within the Lambda function itself and just check periodically for the global store. And again, it depends on what your velocity is. Use a reasonable failure count. So again, this has a lot to do with velocity. Don't overwhelm the system by waiting for 1,000 failures. But if you're 1,000 requests per second, then maybe you want to do something like that. And then understand item potency. This is just the idea that, look, there's anywhere along the chain here something could fail, and so you want to make sure that if you send the same event more than once, that you're not going to cause a problem. By repeating, charging a credit card twice. twice or something like that. And some of these things like Stripe API actually have really good systems in place to prevent that from happening. All right, so what about quotas? So if we think about concurrency, it has no effect on frequency, meaning that even if you set your concurrency to 50, if you're throttling at 250 quota or 250 calls per minute or something like that, it's possible that those 50 concurrent invocations could process more than 5 events in a minute, which means you'd go over that quota. So stateless functions are not coordinated, right? So there's no way for functions to talk to one another. If you use step functions, you probably would get very, very expensive. And if you added state to the individual functions themselves, it wouldn't prevent needless invocations, meaning it would still have to process every request, even if it said, oh no, I can't, or you have to fire off a Lambda function and say, oh, I can't send a request right now. That wouldn't be that great. Is this possible to build? Yes, it is. We don't have time to talk about it, but it's called the Lambda Orchestrator. I have a blog on my site. You can check out that QR code and you can read about this, but this is the way that you can manage that by using a Lambda function to do that orchestration for you. All right, so decoupling our services. I know we're running really short on time. Now, the reason why this is really cool and important is because if you're building an application, let's say it's accepting a order and a new order comes in, you can take that order event and send that into EventBridge and say, okay, we've captured the order, and then you go ahead and reply back to the client and say, we've captured your order. Now, you don't actually accept it into the system right away. You don't process the credit card. But what you do is you go to EventBridge, it's in EventBridge, and now you can distribute it and you can say, okay, I want to send this event into our order service, which you could, again, use some of these strategies we talked about, and you could queue that in an SQS queue, process that off of Lambda, write that to RDS, and have that whole process work there. But then maybe say you want to send a notification, let them know that the order was received, then you can go ahead and create another service called your alerting service, and you can filter that event, send that in there, process that off that SQS queue, just like we did, and maybe you use a Lambda function with a lower concurrency to hit the Twilio API, or you use the Lambda orchestrator or some other pattern to do that. Same thing with the billing service. Send that based off of the event. You can go ahead and put it into the SQS queue, send it into Lambda, or have Lambda process it, write it to the Stripe API. So some really cool things here is that you can add those filters, right? So we can say only send it if the order is complete to the alerting service. Only charge the credit card if the total value is over over $0 or whatever. So you can filter events to selectively trigger these services. You can manage the throttling and quotas per service, and you have the ability to use Lambda destinations with asynchronous events. We didn't really talk about this, but that's something that's really cool that you can look at, ways to forward off messages to other things. So just some other serverless components, managed services you're going to have to deal with and understand the limits of those. Other cloud services like MongoDB or Elasticsearch or anything like that, you're going to have a lot of legacy systems that you're going to have to deal with. You have our own serverless APIs that we've written that may have some limits there. And so those are things that you just need to think about because non-serverless components are inevitable, right? So know the limits of your components, use a good caching strategy, embrace asynchronous processes, buffer and throttle events to distributed systems, utilize eventual consistency. That is this concept of us being able to sort of delay updates to other distributed systems. That's okay, it happens, right? You update your profile picture on Twitter. It doesn't update immediately across everything. It does take a little bit of time to propagate. So just think about that. This is an important one. Listen, thank you so much. I'm so glad that you had me here. This is some information about me, my blog, my podcast, my newsletter, a couple open source projects. Follow me on Twitter, and thank you very much. I appreciate it.
Thank you, Jeremy. And now our next speaker is the VP of Product at Thundra, which is a tool to provide observability and security for serverless and containerized workloads. Being one of the organizers of Serverless Days Istanbul and Serverless Days Virtual, he speaks in conferences and events across the globe quite a lot. We're into a really good chat here about serverless applications and serverless observability. Let's welcome Emrah Shamdan.
Hello, Shift Remote. I'm very happy to be talking to you today, and I'm a bit sad about not talking to you live, but it's a kind of a pre-recorded. And today I'm going to talk to you about serverless observability from development to production. So let's first talk about what is this observability about. So we do testing and monitoring in our monolithic applications, But when it comes to distributed applications, everything is much more unknown. So there might be some failures that we are not even aware of that they exist. And observability aims to understand that type of failures by letting you asking questions. It's for unknowns. So you can understand like the knowns by checking up the metric charts using monitoring, but monitoring gives you necessary material, necessary aggregated and hard data to ask questions. So if we compare observability with monitoring, observability is kind of actually, they are actually different in terms of a word. Observability is a state, while monitoring is an activity. So you can make your system observable by just instrumenting it with some trace, like 3 pillars of observability. We will come later, and it lets you ask questions, while monitoring gives you answers when you just check it. And in monitoring, you are looking at like more like infrastructure level metrics like CPU usage or the memory usage or whatever. Now you look at like application level metrics, traces and logs and the application level metrics. And while the monitoring was mainly an ops discipline, the observability is a development and ops discipline together. So when it comes to this question, is observability possible in serverless? Actually, we have all 3 pillars of observability in AWS serverless together. But not much together, I can say. So we have X-Ray, which provides you tracing. We have CloudWatch logs and metrics, which provides you traces and logs and metrics. But these are a bit like fragmented. They are not actually aggregated together, and it's very hard to understand like which trace actually causes which log items to be printed. And actually, there are also some challenges in observability for serverless. So if you want to install your own agent, it's you don't have any access to underlying infrastructure, and this may be causing some problems for you. And there is an overhead possibility, because like the only time that you can send your data is the execution time, and this will actually cause your function to slow down. And gathering intelligence is acceptable, but for, as I said, it's not very acceptable. Since everything is event-driven and distributed, it's very hard to understand what's going on in this architecture. So before diving into more, let me introduce myself. I'm Emrah Shamdan. I was a developer before I transitioned into a product management job. And I've been a product manager for 3 years, and I'm working as VP of product for Tundra, which is a serverless monitoring and observability company. And recently, I've been selected as an AWS community builder, and I'm the co-organizer for Serverless Days Istanbul and Serverless Days Virtual. You can reach out to me via Twitter or by just sending an email to me. So, like, what we are going to talk in the rest of the presentation, we will first talk about like why serverless observability is that important, what are the 3 pillars of observability, and what are the best practices about them in serverless, and we will talk about hierarchy of observability needs by just relating it to hierarchy of Maslow's needs. So let's talk about serverless very quickly. So in 90s we have physical servers in the room that we are actually locking, and now then we went to the VMs, and then we went to the cloud computing, and now like we are in the serverless area. Everything is now like a single purpose functions doing atomic jobs, and they are integrated together using events. So it is a bit different than what we are doing even with cloud computing, but it is actually, in my opinion, the future of the computing. So serverless can become very complicated. So like for any application, you can start with an API gateway triggers a Lambda function, and this Lambda function writes whatever it does to a database. It can be a PostgreSQL database, it can be a DynamoDB database, and then you start to build some how can I say event-driven applications, and you have Charmeleon. So this Pokemon, if you don't know about the name. In this way, you have a more event-driven architecture, and it starts to become complicated. And after a while, you will need to make your event-driven sub-architectures to talk to each other. And then there are different sub-modules of the architecture here, and they are talking to each other. And this is what we call Charizards for serverless applications. So what we could do to fix the result? Let's talk about observability best practices in serverless. So let's start with the most ancient but actually most useful pillar, logging. So you need to have structured logging instead of just like arbitrary console log lines. You need to have logging which is actually automated, if possible. For example, you can use middleware libraries to automate the logging if possible. And you should have a central ingestion. So you should, if you are just sending your logs to CloudWatch, it's fine, but it's better you send it to some place, and we are assuming that they are structured logs. And when you send it, like, it's automatically indexing these logs. In this way, you can have the good level of understanding of your logs. And if you are using CloudWatch for ingesting your logs, don't forget to retire your logs, because they stay there forever if you don't make any changes, and this can cost you a really big amount of money. So like when we look at the pricing, so ingesting this data is like 50 cents per gigabyte, but like it's storing is 3 cents per gigabyte per month, but like believe me that it's going crazy. So let's switch to metrics. So when you go into metrics, you should keep an eye on critical metrics, and you can ask that, like, what is the critical metrics for serverless? Memory usage is a critical metric, because if your function tries to consume, then it can have an out of memory error. Timeouts are very important, because if your function goes beyond the duration that you designed for it, you will have a timeout error, and your logic will fail. You should look at the concrete executions, because if your function throttles somehow, it can even just like stop while it's supposed to run. And there are also application level metrics. For example, you should look at how many 4xx or 5xx errors do I get, and you should also check out the average MP99 durations to understand if you are close to timeouts or whatever. On top of that, you should have business context metrics, which is like how frequently an event happens. So how frequently your function is getting triggered by one event, or how like you may want to track some of the variable in your application. For example, you can look at the you use Lambda function for IoT purposes, and it can just get the temperature from the remote device, and you may want to look at the temperature of the environment that it gathers data. This is kind of a metric that is related directly with your business. And you should be able to aggregate them into a single pane of glass. So now let's switch to the newest, but in my opinion, the most useful pillar of the observability, tracing. So serverless is so event-driven. As I say, like, remember the Charizard, like, everything is so distributed, and all the messaging is mostly becoming asynchronous. How can you keep track of those? And your services is not just talking to AWS services. They can be talking to a third-party API or non-AWS services as well. So we talked about like logs and metrics and how you are going to correlate those with traces. You should do distributed tracing. So when you look at the distributed tracing issue, there are actually two problems that you need to solve. So the first problem is that how would you produce these traces? Second problem is that, like, let's say you produce these traces, how are you going to visualize them now? So let's first talk about how we are going to generate these traces. X-Ray is a great service, but still has some problems. It still has some problems or getting like stream-based traces. For example, you cannot trace the functions which is talking to Kinesis streams, DynamoDB streams, and so on. And when it comes to async calls, and X-Ray just gives you a kind of a black box when you are talking to an non-AWS service. And as a queue, you can instrument every service yourself, and you should inject relevant data to the spans to make them more meaningful. For example, you can instrument the call to an HTTP third-party API, and in this way, you should also inject, let's say, the payload. Let's say the other data to this span, so you can make them more meaningful. And these are the examples. And you should also inject correlation IDs so that you can understand these two spans are actually related together, because they are asynchronous and distributed. It's actually not very possible if you don't inject any correlation IDs to them. So for just to make it like better and like easier, there are like some open tracing standards. And open tracing is the kind of the start. And now all the observability folks are working on open telemetry, which will make the things even easier. So we should do automated and manual instrumentation together. So if instead of just instrumenting every service yourself, you should use an observability as a service product, and you should let your team put their focus on the value, because this is the first promise of serverless at this place. You should not focus on instrumenting the services. You should focus on what you can do for your customers. And if you want to, do something manual, you should use tagging to embed your business context in traces. For example, this temperature example was one of them. And you can use like user identifiers, event types, your custom KPIs, and so on. And maintaining manual instrumentation is burden. It pollutes the code when you instrument everything yourself. It's hard to test. And it's kind of one more onboarding item for every new engineer. They should understand how you are instrumenting your functions. So let's come to how to visualize the traces. Like you say, when in a typical serverless architecture, you have like 10 functions and like maybe that much of resources, like tables, like buckets or whatever. And you cannot just track. You can track these applications just by looking at charts, because they are now history. You say you have 20 resources to check, and you need to have a very big screen to understand. Now we need to have a time-sensitive flow diagram showing how traces are working. For that purpose, there are some open source solutions, but like they can require modification in your data, and it becomes another thing to maintain. And how we are going to add some custom capabilities like setting alerts on top of them. For that, like there is Jaeger and there is Zipkin, which are very, very good. But again, this is when you start using these open source platforms, again, this becomes another liability for you. So I will just list the best practices for observability from my perspective. So I say, don't try to build it yourself, because serverless is meant to be focusing on the value, not focusing on instrument and observability. And in this way, you will not think about every integration for every new platform. So let's say you started to use a new integration to your application. You will then create another task in your Jira just to instrument this function, this platform. But then, this is actually slowing it down to provide the value. You should take advantage of automated setup and zero maintenance tools like Tundra. And if you really want to do manual instrumentation, you can do this with these kind of tools, but it is something hard, and visualizing it is even harder. So you should have automated alerts, ability to pinpoint the problem, and indexing. So in Tundra, we built this hierarchy of observability needs. So in left, you have all your system components. In right, we list like how you can actually understand what's happening. So let's start from the top. The whole system. As I said, there might be maybe tens of charts, if not hundreds, to understand the typical serverless architectures. So, and it is very hard to understand the issues just by checking the charts by just checking the charts instead of just looking at topology. When with this architecture, we see that there's a problem with Redis by just at a glance. And in this way, you can understand that there is something going on around there. So I'm switching to business flows, and which is like unique traces. So for deleting a team, there is always the same path is being actually followed again and again. But this path is kind of an asynchronous one, and it's really hard to understand like how a business flow performs. So for example, in our example here, it's just like deleting a team, and you see it starts with an API gateway call, and it just like traverses different resources, and it is happening that much of time. And we provide you this view and to understand what's happening. And there are some side effects for this view, so you can catch the security breaches. Like if you see something that you're not supposed to be here, it can mean that like your Lambda functions or your any other resources are actually causing some security breaches. And when you are onboarding new engineers, like by showing them this kind of view, actually will be helpful to onboard them. And you need to have some getting some traction of the high level KPIs, like how many times a team is deleted or something like this. So let's talk about like serverless transactions. So deleting a team was a business transaction, and deleting a single team using this flow is like a normal transaction. And by just looking at distributed tracing, you can understand there's an error and there's a latency. So let's talk about like what happens in a single invocation. So when a single invocation happens, all you have for CloudWatch is actually the logs, but you need to have the metrics. You should have look at the memory usage, CPU usage, and like what part of your function is slowing you down. And in this way, if you have some bad coding practice in code, you can look at this by checking the debugging. In serverless, debugging is particularly hard because when you see a problem, what you need to do is actually you are digging the logs and understanding, maybe guessing the problem and putting a new log in the place to verify your assumption, and you deploy this solution. You see a result, and if you are lucky, you solve the problem. If you are not, you will see another problem, and you will just go over this loop again. Thunder provides you post-execution, in other words, time travel debugging. So even if the application execution ends, we are showing you step by step what's happening in your application. And in this way, you can understand how the local variables are changing, how the parameters are changing, what events are causing which problem to occur, and in this way you can understand what's going on. And we also have a real-time debugging to understand what's going on in your application. With our VS Code execution, you can start debugging your application. For example, here we are just like running the function on cloud, and it is hitting in the breakpoint in your VS Code. In this way, you can understand what's going wrong or what's going unexpected in your application. You can see the event body, and you can see what caused problem, and you can step into your other lines of your code. So let's talk about the key takeaways of today's presentation. Serverless observability is not an after production issue. You should start thinking about observability. You should start how you are going to answer the question and you face problem before production. And you should have all three pillars of observability aggregated for actually responding to issues better. So you can have logs somewhere, you can have metrics somewhere, and traces somewhere, like you can have with X-Ray and CloudWatch. But when they are not aggregated, that's actually can cause some problems for you. You should try to automate yourself, and if you want to ask your questions, you should be ready to ask your questions as well. Instead of just looking at one function, you should look at like a more holistic way and discover the bottlenecks. And serverless transaction is a chain of invocations between resources and APIs. You should have a full tracing for that. And debugging is still required when you need to spot the bad coding practices. Thanks a lot for listening to my talk today. And it was my pleasure to actually give my insights about what can happen in serverless.
Thank you so much for that, Emrah. Now, if you're enjoying the conference so far, remember to let us know in the chat. Are you having fun? Hopefully you are. Now, our next speaker is an engineering lead at Facebook's innovation lab called New Product Engineering. Previously, they were part of the founding team that built WhatsApp Business API. They were the first back-end engineer on Instagram Live and a technical lead pre-IPO hire on Twitter ads. They're currently building a product that will allow the underemployed to earn money by providing online experiences, and somehow outside of this are also a licensed private pilot flying around California. Let's welcome Aman Jain.
Hi, everybody. My name is Aman Jain. This talk is titled Engineering Lessons from the Flight Deck. Here's a bit about me. I live in San Francisco. I'm an engineering lead at Facebook's innovation lab called NPE. Before this, I was a founding engineer on the WhatsApp Business API. I led a team over there of about 5 people. A little before that, I worked at Twitter and I led a team of about 5 people over there as well. Very relevant to this talk, I'm also a private pilot. A private pilot means that I can fly for fun and carry passengers, but I can't charge my passengers, which works out really well for my friends. I earned my license about 3 years ago. It took me about a year and a half to get that license. So let's start with a hard fact. The consequences of making mistakes in aviation are very high. People die. There aren't very many other professions in which this is the case. Aviation is also very complex. But despite being inherently risky and complex, aviation still remains the safest mode of transport. I looked at the latest safety numbers and I found that airlines have more than 60 times fewer fatalities than driving a car. What makes aviation so safe? What makes aviation so safe is its culture of learning from its mistakes. Each and every reported accident, no matter how small or big, is thoroughly investigated. Based on these investigations, the Aviation Authority comes out with new rules and directives to try to eliminate the entire classes of errors from happening again. This culture of learning from mistakes has propelled aviation to lead the way in safety, robustness, and better engineering. During my training, I learned a lot of these lessons firsthand. I was also amazed to realize that a lot of these lessons could be applied to my day job. They helped me become a better leader at Facebook. Today, I'm going to share 3 of these lessons with you. The first lesson is respect the craft. Let me explain. When I first started flight training, this is kind of the image I had in my mind. I also had my aviators on, and the Top Gun background score was playing in my mind. But the reality turned out to be a little different. I learned that there are certain elements of piloting that are not as exciting as the rest. Before even sitting in the aircraft, all pilots go through a thorough inspection of the plane. This is called a pre-flight. As part of this pre-flight, student pilots in my flying club were required to clean the windshield. To me, this seemed like boring work, and sometimes I would skimp on it. And my instructor wouldn't always fail to remind me that a clean windshield will help us spot other airplanes more easily and hence lead to a safer flight. But I would do it half the time and not do it half the time. But one day he said something which I thought was very profound. He said that I've found that students who do a better job in cleaning the windshield turn out to be better pilots. Somehow that day it clicked in my mind. Cleaning the windshield is not just cleaning the windshield. It's a metaphor for the mindset of the modern day pilot. Piloting is no longer the cool adrenaline pumping activity it was during the early days of aviation. Nowadays, a lot of the emphasis has shifted towards maintaining operational excellence, following standard procedures, and doing the small things right. Cleaning the windshield metaphor applies aptly to software engineering as well. When one of my mentors at work was leaving the company, I asked him to share any parting wisdom on how to build the best software engineering team ever. He said something very simple. He said, everybody knows what the best practices in software engineering are, but nobody wants to spend the time to follow them. If you follow the best engineering practices, you will become the best team. In other words, similar to aviation, it's important to spend the time to work on some of the unappealing aspects of software engineering. Here are some examples of what I'm talking about. You should make sure you're cleaning up unused code. You're spending the time to write specs for features and keeping the specs up to date. You should make sure that you're ensuring your build and deploy is a single step, or ideally continuous. You should have good test coverage and your tests should not be flaky. And you should make sure that you're spending enough time in writing the code for your internal monitoring and debugging tools, and they're as high quality as your external code. If you want more information about this, I would highly recommend you read the book, The Pragmatic Programmer. But that's not my primary point. My primary point is that everybody knows what the best practices are, but most teams don't follow them. The secret to becoming a good engineering team is respecting the craft and doing the small things right. The second lesson for today is communicate clearly using a shared vocabulary. Let me explain. Nothing makes you feel more like a pilot than talking to air traffic control on the radio. Have a look.
Alpha departure. Squawk 1541, verify Yankee, please.
Yeah, Yankee and after J174 to Wilmington. What was the next six prior to AR3?
Charlie Lima Bravo.
Okay, clear to Providencial is Kennedy 1, runway heading 1.5, turning 100, radar vector is wavy, direct J174 Wellington, direct Charlie Lima Bravo, AR3, new car, Lima 463, maintain 5,000, 36 and 10, 154, 114.
Unless you're a pilot, I'm sure you didn't get half of that. But to a layperson, this aviation lingo sounds really cool. And for pilots, that's probably part of the charm. But even though it sounds cool, that's not the goal. The goal of radio communication is to communicate with brevity while being as accurate as possible. Brevity is important because all aircrafts in the same area are typically talking on the same frequency. So if you're long-winded, you're taking away valuable on-air time from other pilots. Even more than brevity though, it's important to be as accurate as possible so as to avoid any miscommunication. Everything in radio communication revolves around these goals. Here's some example. You might already know this. In aviation, we use the NATO phonetic alphabet, like Alpha, Bravo, Charlie, Delta. This is used to transmit any important information. And the main goal is to make sure people don't get confused between phonetically similar sounding letters. Another example is how you pronounce numbers. So when the controller is conveying something important, like the wind direction, they always say individual digits separately. For example, they would never say wind direction is 320 degrees, because it's possible that the audio cuts out in the middle and the other person thinks that you're just saying 300. So suppose you're saying 320 and the audio cuts out in the middle, it's like 300, which is really confusing and can lead to accidents. Instead, they will always say wind direction 320, and the other person's always expecting 3 digits. So if they miss one, they know there was a communication error and they can ask again. So these are interesting examples, but what I find even more elegant and transferable to software engineering is the use of specific phraseology in aviation to mean very specific things. When the controller says hold short of position, the instruction is very clear. There is no confusion if you need to stop before the position or at the position or after. Hold short of position means it needs to be always before. Another example, climb and maintain new altitude, very tersely conveys that you need to climb and then stay at that new altitude. It doesn't leave any room for interpretation about what to do once you reach the new altitude. Similarly, when the pilot says Mayday, 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 the receiver instantly knows that there is an emergency without having to guess the severity of the situation. Okay, so that's cool, but you might ask, how is this related to software engineering? I found a need for a shared vocabulary in software engineering teams as well. From my past experience, it's very common for engineering teams to ask questions like, hey, is task X complete? Or how long will it take to do Y? This opens up room for miscommunication because of differing definitions of complete. One person's definition of complete might be that the basic functionality is done, whereas another person's definition of complete might be that the product is thoroughly tested, all edge cases are covered, including error retries. You can imagine that these two people will have very different answers to the question, is X complete? Or also very different time estimates when somebody asks them, how long will it take to do Y? This is a big problem and can lead to miscommunications. But the good news is it can also be solved with the help of a shared vocabulary. Let me share an example of a framework that my team started using to decide what level of polish we want for different features. So this framework is called the Levels of Polish framework. The first level is functional. This means that the user can complete the basic task. For example, suppose we're building a flow to upload a picture in our mobile app, then level 1 would mean that the user can post a picture on the app, but nothing more. Level 2 stands for polished. This would mean that the user finds the experience well done. In our example, this would mean that when the user posts a picture, they see a progress indicator. Once the post is successfully uploaded, the user receives both visual and haptic feedback. And then level 3 is the highest level. It stands for delightful. This means that the user experience is elevated to the next level. So in our example, this would mean that the user finds the upload speed very fast because the picture is optimistically uploaded even before the user presses a button, and all corner cases are covered. The network errors result in automatic retries, and if there's no network, then the post is saved as a draft, so the user can get back to it later. That is delight. So we use this framework in our team to align on what level of polish we need for different features. We typically shoot for level 3 for the main features that the user really comes to the app for. And then for some of the not so important features like the settings tab, we aim for either level 1 or level 2. But it doesn't matter what levels you decide on. But what's more important is that your team uses some shared vocabulary so as to avoid any miscommunication. Awesome, let's get to the third and final lesson. The third lesson is have clear owners. Let me explain. As part of flight training, all student pilots are supposed to read the Federal Aviation Regulations, also called FAR. These regulations are prescribed by the Federal Aviation Authority, or FAA, and they govern all aviation activity in the United States, from small planes to jumbo jets. It's, as you might imagine, it's a very long and dry read, like most legal documents go. However, there's one regulation in there that I find very powerful. The Federal Aviation Regulation states this: the pilot in command of an aircraft is directly responsible and is the final authority to the operation of the aircraft. In an in-flight emergency requiring immediate action, the pilot in command may deviate from any rule of this part to the extent necessary to meet that emergency. That's a lot of power vested in the pilot of command. Not only does the pilot have full control of the aircraft, they also have advance permission to break any rule in the book in case required for an emergency. Why does the FAA do this? The FAA does this based on the belief that nobody involved has a better assessment of an in-flight situation than the pilot themselves. Having complete authority helps the pilot respond faster to emergencies. It also cuts down on deferred responsibility, which is a psychological phenomenon where people are less likely to take responsibility when other people are present. Clear ownership is equally important when leading engineering teams. On the surface, this piece of advice often comes off as trivial and already well understood. I also felt the same way until our team decided to follow a formal framework to measure our team health. As part of this framework, we all filled out something called a discovery sheet. as this picture on the slide. In this sheet, we had to list down each and every single area that the team owned. And then for each area, we had to write down every single feature as individual rows. And then for each row, we filled out columns like who's the primary owner, what alerts do we have, what's the test coverage like, how many bugs, and tech debt. We found that most assets had clear owners, as we had expected, which is good. However, it was eye-opening to see that few features, especially the ones that lay on the boundaries between our team and a partner team, like a thrift service or an API, had unclear owners. Our teams felt that the other team was responsible for them, and they felt that we were. So it was in this purgatory. It was also interesting to find that the features that had unclear owners were also the most buggy. Once we clarified the owners by working with our partner teams, the bugs decreased and the features improved drastically. Great, so we covered 3 lessons. To summarize, I spoke about number 1, respect the craft, doing the small things right. So number 2, communicate clearly using shared vocabulary, which means having the same definition of done. And number 3, have clear owners. Set the right context and encourage the owners to make the decisions. Great. I'd like to end the talk by making one last point. In aviation, the consequences of making mistakes are very clear. People die. This skin in the game has propelled aviation to lead the way in safety, robustness, and better engineering. In most software companies, the stakes don't feel as high, and often there are good reasons to trade off quality in place of speed. However, it's important to realize that software is eating the world, and a lot of people are relying more and more on software to do critical things in their daily lives, especially post-COVID. For example, when your video chat software has a bug, that's not a mere annoyance anymore. It prevents you from doing some basic stuff in your life. I hope this empathy with your customer pushes you to take pride in the craft of software building and to strive for excellence. Thanks a lot for listening. My name is Aman Jain, and I'm happy to discuss any of this further. Feel free to connect with me on Twitter. My handle is ajain. Thank you.
Thank you for that, Aman. Now, one of my dreams is to fly a plane, and I'd love to be able to do that is really all I've got to say here. Aman, what I'm trying to say is I want to be like you. Now, anyway, our next speaker is a head of Atlassian development at Venature, and for the last 2 years has been focusing on developing viable and complete IT solutions to the Atlassian marketplace. Aside from the Atlassian ecosystem, his interests are occupied by streamlining and optimizing software, and when he's not doing that, he finds the time, as we all do, don't we, to browse the internet, discussing the latest news in the tech world, and of course, gaming. Our next speaker, let's welcome Tomislav Nikolic.
Hello, everybody. My name is Tomislav Nikolic. I am an Atlassian app developer at Venature. My talk is going to be about Atlassian Forge. Before we get that started, though, let's talk about Venature a little bit. So Venature was founded in 2016 in Cologne, Germany. What we do is we supply and implement customized solutions for all Atlassian products through consultation, distribution, and technical services. We currently have offices in 3 countries, Cologne, Zagreb, and Turkey, Croatia, and Turkey. And throughout these, we have over 50 employees. Also, Venature is one of the fastest growing Atlassian solution partners worldwide. And that is why last year the Atlassian Partner of the Year award was awarded to us in category Rising Star EMEA. In addition to that, at the beginning of 2020, we became one of the first Infobip solution partners. So let's get to the Forge. So what is Atlassian Forge? It is an app development platform designed for customizing, integrating, and extending Atlassian cloud products. With Forge, Atlassian aims to reduce some of the complexity that developers face when they are doing cloud development. To see how they're trying to achieve that, let's go over some features. So first of all, it's the Atlassian hosting. With Forge, everything is hosted by Atlassian, and the Forge's serverless model enables developers to write single functions rather than entire web applications. And this problem is very pronounced to whoever wanted to build like a simple app that just does like a button click or something. And while we are speaking of that button needed to be stylized somewhere, it needed to be defined, and the click on the button needed to be handled. With Forge, something like that is just a matter of importing a Forge UI component. And last but not least, the developer experience. With Forge, the only tool you need to deploy, test, debug, and monitor your app is Forge CLI, which is a command line tool that enables you to do all of that stuff. And we'll go over some of the basic commands later on. Next, let's take a look at how Forge is changing cloud development significantly for Atlassian products. What it does, it allows developers to focus more on building functionalities, bringing value to these products, instead of having to manage their security or having to build an infrastructure for testing, staging, and finally hosting their app. In software development, we call this moving up the stack. When we do not have to care about platform details or implementation details of the code that we write, and we just want to focus on building those features and getting to the products. Before continuing on with Forge and what Forge looks like in action, let's talk about some limitations and requirements of Atlassian Forge. Before you can do anything right now with Forge, you would need to join the closed beta. And you can do that by joining the waitlist at atlassian.com/forge. Now, whoever has faced with Atlassian cloud development knows that the recommended way to build cloud apps is Atlassian Connect. And what Forge is, it's not like a replacement for Atlassian Connect frameworks. It's more supplementary to Atlassian Connect. And not yet available, but Atlassian is working on it, is the marketplace support. And they're also working on getting Atlassian Connect to work with Atlassian Forge and form a single development experience. That is why it's crucial for developers and integrators to try out Forge and bring that feedback to Atlassian, which they're anticipating and listening to during the beta. Now, with that out of the way, let's look at what Forge actually looks like in action. Before you begin for actually starting with development, you will need an Atlassian Cloud instance. And you can sign up for a free development instance at goatlassian.com/clouddev. The link is right there, and the sign-up process is as easy as 1, 2, 3. You just need to define your details and the URL that you want for your cloud development instance. Following, you will need to get Node.js and Docker, and Docker is going to be used to actually tunnel the invocation of the app to your development machine. And Node.js will be used to install Forge CLI and Forge UI. Now, all of the following information is also available online. I just wanted to stress how easy it is to get started. That is, once you're invited to the beta program. So let's see what creating a new app looks like. First, you will have to log in by running Forge login, and that's going to be your Atlassian account details and the API token that you can create. Next, you will want to run Forge create, and this will ask you about a couple of details for your new app. Some stuff like name and the project template that you will want to use for your beginning, for your new app. And finally, running Forge deploy will just deploy the Atlassian, deploy the app to the Atlassian's infrastructure. All right. How about installing the app? We've deployed it. We want to get it installed. The next thing you'll want to do is run Forge install. And the next thing that Forge CLI is going to ask you is ask you to provide the details of your development cloud instance. And once you do that, it's gonna run some error logs, whatever, and it's going to be installed on your development instance. Let's talk about Forge Tunnel for a little while. You can see in the video that I'm running it, and what it does is it creates a Docker image, which will tunnel to the development instance or any instance where the app is running. So this will allow us to develop a lot faster than changing the app, then deploying it again, and repeat the process all over again. So it's a neat tool that Atlassian has bestowed upon us. And this is, again, going back to that infrastructure. The developers do not need to set up anything. It all comes working outside of the box. So you have your app installed and hopefully tunneling on your development machine. So what's next? I couldn't possibly fit anything that I want to say about Atlassian Forge because it's pretty exciting. I have been doing server development mostly for Atlassian server products, and I have recently started to dabble into Atlassian Cloud. And it's really fascinating how far they've come in supporting their developer community. So for anything that can be found on these links and you have more questions, I'll be happy to help you. But other than that, the Atlassian documentation is very well written on Forge, and even if you're not familiar with some of these technologies, these examples will get you up and running in no time. For more information, you can check out Venature at the address right there, venature.net, or you can contact us via the email addresses provided. And I would like to thank you all a lot for your attention, and have fun working in Forge. See ya.
Thank you, Tomislav. And it is now our break. This is literally just 5 minutes, so do not run away or else you will miss the rest of this incredible conference. But it wouldn't be a break if we didn't use that break coming to our website to check out what's coming up next for Shift, which is Shift Money, which is our in-person conference held in Zagreb on the 7th and the 8th of December. Please do go and register there on our website. You'll find more information and all the details there. But grab yourselves a drink and we'll see you again in 5 minutes' time to carry on with the rest of our conference.
Uz moja RBA mobilno bankarstvo prati stanje svojih računa, plaćaj putem fotonaloga, upravljaj svojim troškovima ili šalji novac svim kontaktima iz mobitela uz ClickPay opciju. A od sada svaku transakciju iznad 300 kuna provedenu kreditnom karticom možeš podijeliti do čak 24 rate. Doživi taj RBA osjećaj. Uz moja RBA mobilno bankarstvo prati stanje svojih računa, plaćaj putem fotonaloga, upravljaj svojim troškovima ili šalji novac svim kontaktima iz mobitela uz ClickPay opciju. A od sada svaku transakciju iznad 300 kuna provedenu kreditnom karticom možeš podijeliti do čak 24 rate. Doživi taj RBA osjećaj. Uz moja RBA mobilno bankarstvo prati stanje svojih računa, plaćaj putem fotonaloga, upravljaj svojim troškovima ili šalji novac svim kontaktima iz mobitela uz ClickPay opciju. A od sada svaku transakciju iznad 300 kuna provedenu kreditnom karticom možeš podijeliti do čak 24 rate. Doživi taj RBA osjećaj.
Welcome back after the break. If you can hear my voice, that does mean that your 5-minute break is over. I know that time flies, but what is also great about that is that you're back here with us to carry on with our conference. I do hope that you're able to register for Shift Money. If you haven't already, please do. This is your reminder, and continue to use the hashtag ShiftRemote for any social media posts about this event. Let us know what you think. We love it when we see and hear from you all, because you, our audience, make this the conference that it is. Now, our next speaker's life is centered around technical leadership, developer communities, and free open source software. Their daily job involves running startup engineering teams, twice already with an exit, and now on the third run, building enterprise products. During their spare time, they focus their passion to energize the developer communities by sharing insights on a blog and speaking, as all of our speakers do. Our next speaker, let's welcome Arya Hidayat.
Hi everyone, thanks for being here with me. My name is Arya, and today I'm going to share with you some of the experience that I had doing a lot of testing for some Firebase projects. Now, as a disclaimer, I do not work for Firebase. I do not represent Firebase or Google in any capacity. This is just me trying to share my experience as a happy user of Firebase. When we mention Firebase, usually what people have in mind is backend as a service. Now, there are many services from Firebase that you can use. For this talk, we're going to cover the testing for 3 important Firebase services: the hosting, the functions, and the database itself. Now, let's get started. Before I continue, I created a sample Firebase project that you can look at to serve as your reference if you want to come up with your own tests. This exists in at github.com/arya hello-firebase-experiment. This is a very simple Firebase project. It does almost nothing useful, but surely it serves as a good reference. Now, the first thing that we want to test is hosting. Hosting is nothing but just serving static pages on the website. Usually when you use Firebase hosting, you deploy to Firebase, but you also point Firebase to your own custom domain, and then it serves as a nice static website. For testing it locally, fortunately, there's a Firebase emulators. And if you configure your Firebase JSON correctly, all you need to do is just running emulators. Because I wrap Firebase in a scripts inside package.json, I can easily run this as npm run firebase -dash emulators :start. So what this command will do is to launch Firebase emulator, which will take a look at your firebase.json configuration file and then find the static files that you need to host. Obviously, this is through the emulator, so locally, and then launch an HTTP server at the specified port. You can configure this, but I find out that the default 5000 works well. Now, after the emulators is launched and start the servers, you can open your web browser and point to that address, localhost port 5000. Now, as soon as this happens, you can perform all kind of manual tests by just exercising or going to that URL. And if you have some automated tests, maybe it's Selenium, maybe it's Cypress, or any kind of other framework, you could do that as well just by using this URL of the local HTTP server. If you want to run automated tests in the CI system, you could start the emulator this way, you run the tests, and then kill the emulator or shut it down. In other words, for hosting, it should be very easy because it's nothing but just HTTP server serving some static files. Functions could be a bit more challenging, and the first thing that I usually do whenever I need to implement some business logic in Firebase functions is to implement some very simple health check. I usually call this ping, but you can call it health check or any kind of other name that makes sense for you. And the goal is very simple. In any kind of testing process, before we go on and exercise the more complicated business logic, first thing that we need to do is to call this function ping and to make sure that it works. Because if it doesn't work, usually something happens there. Maybe some misconfigurations, or you deploy to the wrong environment, productions versus staging, and so on, and many other different reasons. So a simple function that almost does nothing useful, but just sending the OK response, will be a nice litmus test or serve as a canary. Also, I find out that sending more than just OK will be a bit useful. For instance, oftentimes I just send the timestamp when this function is being executed. That allows me to troubleshoot whether this health check function has a stale response because maybe it's cached somewhere incorrectly. And then that allows me to distinguish between a fresh response that just happened a few seconds ago, just by the virtue of looking at the timestamp in that response. Once this is done, then you should use whatever test framework that you have inside your Firebase project to implement the testing for this. And that's very simple. In this case, I use Axios to run an HTTP GET request to this particular URL, localhost port 5000/ping, which is the URL that's served by a Firebase function through the emulator for local testing. We just need to pick up the response, split into two parts, the OK parts that we will match against the OK constant, as well as the timestamp part that we will match to a regular expression that indicates a series of numbers. Now, if we have this and we run this, we're gonna get the result. Some trick here is that instead of just using emulator start, we're gonna use the command emulators exec. The beauty of this command is that Firebase will start the emulator, run the command that specifies after exec, and when that command is completed, shut down the emulator automatically for us. This is fantastic because whatever tests that we want to run, in this case Axios exercising the ping function, can be packaged as part of npm test. In my example here, npm test will just run npm Jasmine because this sample project uses Jasmine test framework, but you can use Mocha or any other test framework. Again, the step is Firebase is going to launch the emulator, set up everything, including the local HTTP server and the functions emulator, run the command which we specify, and then when the command is the test command is completed, shut it down, and then we're done. With this simple trick, we can incorporate this single line in our CI system, and therefore it bakes in the complete test for your functions, although in our case here it's just one function for now, into the entire CI process. Now, that is easy: hosting, serving static pages, functions, running some business logic. But what about something more complicated? What about something that has some persistency, such as a database? Here we're using Firestore as an illustration, but the principle works for any kind of other database supported by Firebase. Now, let's imagine that there's a simple database under the name collections universe, and the document is called answer. Again, Firestore is a document database and NoSQL, so it's not relational. Imagine that we wrap this into a function. So there's a function called answer, which just pick up the value inside the collection called universe and the document called answers, and then return it, which as an HTTP response. However, if we try to run this with the same command that I mentioned before during our testing of function, npm run firebase npm test, unfortunately it's going to cause some error. Cannot read property value of undefined. And this makes sense because if we launch an emulator, the database is empty. The Firestore database is empty. And therefore, when it tries to fetch the collection, obviously it's going to fail. And because the collection doesn't exist and it causes some failures, we end up with this type of errors. So how do we solve the problem? Well, there's only one way to do this, right? We have to pre-populate the database, our Firestore database, with the proper collection and proper document. In order to do that, we can use the so-called Firebase emulator suite. There is a complete and comprehensive documentation at the Firebase website about this. Basically, what we need to do is to launch the Firebase emulator suite, create the database Firestore with the collection and answer that we want, and then as soon as we populate it, we want to capture it as a test fixtures. And the way we do this is, while the emulator suite is still running in the background, on the command line or terminal, we also call this emulator :export. Now, if we do this, the effect here is that the entire thing, the entire Firestore will be exported into a fixture. In this case, I call it spec/fixture. Now, when this happens, we can later on use these fixtures, import it before running the test. And that's exactly what we do here in the screens. npm run firebase --emulator exec with npm test, but we have additional command line argument here, -import spec fixtures. Now, same thing as before, when Firebase launched the emulator, it's going to start the local HTTP server for hosting. It will run the emulator for the functions, and then it will run the emulator for the Firestore. However, before anything is started, every collection and documents that is specified as the fixture will be imported, hence the name, to Firestore. In other words, by the time npm test is executed, the database is not empty. It actually contains a collection and documents that we specify when we manually create this to the emulator suite. This is why the test will pass now, because basically our test is grab the collection called universe, find the document name's answer, and fetch the result. And the result is obviously what we wanted here, coded in our test. So that's the simple steps to utilize the emulators to capture the snapshot or the content of Firestore database and export it as test fixture so that we can run it as part of the emulator execution through npm test. This is obviously along with the hosting and function that we covered earlier. To summarize, we can also put this together in a CI system. For instance, I use here GitHub Actions, but any kind of CI system, be it Jenkins or Travis or Circle CI, should work equally well. What we do here is check out the project, pick up Node.js, and then install the dependency through npm CI, and then run this entirety of the command that I mentioned earlier. Emulators exec, which run the test suite, And then we also need to import the fixture for our Firebase Firestore. Now, with this, you completely implement a CI system for your Firebase project that covers all the testing for hosting, for functions, and for Firestore. Hopefully that's going to be useful for you. If you have some questions, find me on Twitter at Arya Hidayat. Thank you so much.
Thank you for that, Arya, and we have another speaker lined up for you. But before we get to our other speaker, I want to check in with you all, because I'm that host, and I want to know how much you're enjoying the conference, and I just want to hear your words there in the chat. I want to see all of you telling us that you're having some fun, because it wouldn't be a conference if we weren't engaging, right? And in this virtual world, it's so important that we continue that energy and continue to engage. Now, our next speaker, this bio, I absolutely love it. Why? Because there isn't that much there for me to read. Our next speaker is a Spring enthusiast, occasional infrastructure abuser, and basically a computer geek. They're a senior Java engineer. Let's welcome Zeljko Margeta.
Hi and welcome to another Shift Remote Talk. My name is Zeljko Margeta. I'm a Java developer working at Raiffeisen Bank, Austria, and today I will be talking about serverless. Now, I've had issues with understanding what would serverless mean for quite a while. I mean, surely there are servers involved somewhere, right? Why call it serverless then? This must be just another marketing buzzword. And then I came across this definition by Ken Fromm after watching a talk on serverless by Sam Newman. It says the phrase serverless doesn't mean servers are no longer involved. It simply means that the developers no longer have to think that much about them. And it kind of hit me. The developers no longer have to think that much about them. I like that. Now, mind you, the keyword here is developers. It basically means you're paying someone else to think about this stuff for you. Also, most likely somewhere outside of your organization. And it was an epiphany. I am a developer and I don't like thinking about this stuff. At least not to an extent required for running it on premise. And that brings us to the next issue that was bothering me about serverless. 100% of developers think of AWS Lambda when talking about serverless. By the way, I made this up, but from my experience at least, Lambda is practically a synonym for serverless, or Azure Functions, or Google Cloud Functions for that matter. Maybe I should have put Functions as a service instead of Lambda here, but you get the idea. And that was the issue I was having. I didn't want to rewrite my code to be function as a service friendly. I like Kubernetes, I like containers, I like the abstractions and the development flow that I was used to. And maybe the most important thing, I didn't want to go all in on serverless as I understood it then. I didn't want to move my database to DynamoDB or something similar, just to make sure my functions don't overwhelm it. So I dismissed serverless and went on with my life. Then I stumbled upon AWS Fargate. Now, I'm talking about AWS because it's the cloud provider that I'm mostly familiar with. I'm sure the other big two have something similar to offer. I'm not biased by any means. Anyway, I started reading about Fargate, so I could use it with AWS EKS, which stands for Elastic Kubernetes Service, which is a managed Kubernetes cluster. Managed meaning I don't have to tinker with it, so that's a good start. Now, what Fargate brings to the picture is serverless. Well, at least by the definition that I like, meaning that I don't have to manage the worker nodes either. It all automatically works out of the box, so I can focus on building my services. Now, another big selling point, for me at least, is that you pay for the resources you use and when you use them. Another thing that I would like to add to my serverless definition. It's not quite Lambda pay as you use, but it comes pretty close. And it uses Firecracker underneath, meaning that my containers are really isolated, drastically reducing the attack surface. I really like containers, but I have to admit that security-wise there are issues which Firecracker here resolves. And that was it. I was hooked. The dilemma that I was having in my head, serverless versus containers, went away. I could get the best features of both worlds. Life was good once again. Now, the most interesting thing about Fargate for me was the use of Firecracker to provision micro virtual machines, which are then used to run your containers. Each Firecracker micro virtual machine runs a single container, which, in my opinion, is a big improvement compared to non-Fargate workers, where each container would be ran inside a full-blown EC2 virtual machine instance. Fargate work runs as a fully managed EC2 instance, and in turn it runs multiple Firecracker micro virtual machines that in turn run your containers. What all this means in the end is you don't have to allocate your resources to maintenance, patching the operating system, upgrading Docker agents, upgrading ECS agents, or worry about scaling. And we all know that scaling is not a trivial thing to do. You most likely will have to do several iterations before you get it right. This also means your operations team is freed up to do the cool stuff instead of the repetitive mechanical steps required to maintain your infrastructure. What this means is that your containers are properly isolated at the virtual machine level. This is a proven and battle-tested isolation technology. Now, each Fargate instance has its own elastic network interface that the micro virtual machine can't access, meaning that if compromised, it can't really do much. This also means more fine-grained CPU and memory options, allowing you to better size your container requirements, which in the end means less overhead that you end up paying for. Now, I don't know about you, but it all sounds pretty good to me, not only from a developer perspective, but for your entire organization. But you know, all these buzzwords got me thinking. What are we talking about is basically different levels of abstraction. First, we started with bare metal deployments, where you had to manage everything from basic hardware and operating system, all the way up to the application server, or whatever you needed to use to run your applications. Then infrastructure as a service came along, meaning you could push a button and get a virtual machine. I mean, you still had to manage the operating system and your application server, but at least you didn't have to deal with hardware anymore. And by the way, I know this is a very developer-centric view. Some of my friends from infrastructure were probably not like this at all, but we're on a developer conference after all, aren't we? Then Docker came along and turned the world upside down, so we got containers as a service, meaning you could use a container as your abstraction, your unit of deployment. And then finally functions as a service came along, where your abstractions were even smaller, compressed to a single function. Now, to be honest, I thought we went too far with functions as a service for a long time, but I managed to see the use cases and came to appreciate the ES offering as well. After all, I'm a Java developer and I have my own selfish reasons for not liking or even understanding Lambda when it first came out. Let's be honest, Java isn't well known for fast startup times and low memory usage. Now, GraalVM and native compilation is changing all this, but this is probably a subject for another talk. So, back to my story. All these abstractions levels reminded me of something else, something that was closer to me, something I understood better. And there it is. Am I right? Now, I added garbage collected languages as a category since they allow you not to think about memory as much, but this is really similar to the previous slide, isn't it? If you ask me, it all comes down to evolution and picking the right tool for the job. Another interesting thing I noticed is that the higher you went on the abstraction, the more you got looked down by the people who remained on the lower level, not considering you a real programmer because you used a different level of abstraction. I guess this is a circle of life in a way, and I kind of see this happening on the infrastructure part as well. But anyway, I digress. 100% of IT professionals will pick the right tool for the job. Yet another statistic that I made up, but if you take anything from this talk, I would like it to be this: pick the right tool for the job. And don't be afraid of vendor lock-in. You might be losing more by not taking advantage of the new technologies than by possible future migrations. As Sam Newman said at one of his talks, there are walled gardens and then there are walled gardens. Take Apple for example. It's a walled garden, but it's a pretty nice one, wouldn't you agree? Same goes for cloud providers. You might be missing out on a lot if you're afraid of the change because it might possibly cost you in the future. Now, this is especially true for AWS EKS, since there are plenty of cloud providers that offer a managed Kubernetes solution. If all goes south, you can always run it on premise, as we are doing at the moment. And that brings me to the banking industry. If I asked you to think about the most regulated, most old school, most things never change industries, banking would probably be in the top 3. Am I right? And 5 years ago you would probably be right, but things have changed. And they have changed drastically, believe me. I remember deploying to AWS application servers, being limited by the available libraries, always waiting for something to be upgraded by the vendor. But the IT in the banking industry is a very different beast now. I can tell you about my bank in particular. We are running Kubernetes clusters in production. We have event-driven microservice architectures. We're utilizing Kafka, Postgre, MongoDB, just to name a few. We're building our own machine learning models. We have continuous integration and delivery pipelines all the way to production. We practice DevOps. You name it, we're probably doing it. You know, the good stuff. So being a developer in a bank today does have its advantages. Which brings me to the second part of my talk. Where does serverless fit into? Now, if you were a startup or starting an isolated greenfield project, I would tell you to go all in on the cloud. Preferably use serverless. It will save you a lot of work up front and allow you to bring your product to the market faster. But with banks, the situation is a bit different. There are quite a few legacy products. I mean, the bank has probably been around for some time. So the answer isn't so straightforward. But this doesn't mean you shouldn't consider the cloud or even serverless for that matter. Take for example our PSD2 integration. It is running in the cloud, fully integrated with our legacy systems. Learn to pick your battles and choose the projects that will benefit the most from your decision. Pick the right tool for the job. I am fairly convinced that the future is the cloud even for existing established industries, as is the banking industry. Another good pick for migration to the cloud are your development environments, your continuous integration and delivery pipelines, proof of concept projects, pretty much anything that would benefit from a fast return on investment. Plus, it will make your developers happy and probably cut down on some of the red tape, making you more agile. And we're all in the agile business, aren't we? So, that concludes my talk on serverless, but what kind of a developer would I be without a demo? I have prepared a small demo on serverless, AWS EKS and Fargate to be precise, showing the deployment of a small Java service, including the setup of infrastructure. After the deployment, we will tweak the number of instances and see how Fargate deals with it. So let's dig in. We will set up a new EKS cluster within its own virtual private cloud. I already deployed this part since we don't have much time and it takes about 10 minutes or so to set it up. Worker nodes will be managed by Fargate inside the private subnet with the net server sitting in the public subnet. Now, I decided to use Pulumi to describe the infrastructure as opposed to using Terraform, which is a more mainstream solution. The main reason I did this was because I found Pulumi to be more developer friendly. It allows you to use software development kits for multiple programming languages, including Python and TypeScript, to name a few. The reason I'm using TypeScript for this demo is because the Pulumi crosswalk for AWS doesn't have the Python implementation yet. Pulumi Crosswalk for AWS is a collection of libraries that use automatic, well-architected best practices to make common infrastructure as code tasks in AWS easier and more secure. So we have that covered as well. Anyway, we defined the virtual private cloud and deployed an EKS cluster to it. The control plane is fully managed, and we defined the kube system and default namespace to be managed by Fargate. This means our service containers as well as core DNS containers will be managed. Now, one of the current shortcomings of Fargate is that elastic load balancers are not supported out of the box yet, so we'll be using an application load balancer instead. This means we have to deploy the ingress controller and the ingress to our Kubernetes cluster ourselves. This isn't too much work, it mostly comes down to setting up the correct AWS policies and roles for the ingress Kubernetes service account. Okay, so let's take a look at the code. The Spring service is a trivial REST service that returns a collection of greeting messages. In this case, just this hard-coded one. I could have probably put all these classes in a single file for demo purposes, but I suppose the years of reading about clean code and architecture best practices got the best of me. So there it is. It's a reactive web service running on Java 14 and built using Spring Webflux and Project Reactor because YOLO. I'm using Jib to build and deploy the Docker image to my Docker Hub repository, And apart from that, there isn't anything too interesting about the service itself. I can show you the Kubernetes deployment and service definitions I used for local testing on Kind, so we can compare them to Pulumi definitions later. I also defined the liveness, readiness, and startup probes, which are just hitting the health endpoint provided by Spring Boot Actuator. And here is the Gradle build file for completeness. Now, the more interesting part for this talk, anyway, is the infrastructure definition. So let's take a look at what does this look like in code. We start off by defining the VPC with a private and a public subnet and 2 availability zones. The tags here are required by the AWS Application Load Balancer English controller. Next, we define the EKS cluster itself. By the way, I find it fascinating that the Pulumi guys made selecting Fargate a simple flick of a Boolean flag. Next on the list is some ALB related bookkeeping, the AWS IAM policy, and hooking up the right roles to the right accounts. Nothing too exciting here. Then we deploy the application load balancer using Helm, which simplifies the process a lot, and this is what is running on AWS so far. We can check out the current state of the cluster. As you can see, there are 3 Fargate nodes. Those are completely managed, and Core DNS and ALB ingress pods are running inside the kube system namespace. Now, as far as the default namespace goes, it is empty at the moment. Okay, so since our EKS cluster and ALB ingress controller are deployed, we can now deploy our service. Pulumi takes care of only deploying the diff in the same way that Terraform does it. And as you can see, there is no AWS specific configuration, only classic Kubernetes definitions, slightly altered to fit the TypeScript SDK. You can use the quote-unquote raw Kubernetes YAMLs as well, but I thought it might be a good idea to show how it might look like using the SDK constructs. Spoiler alert, it looks pretty much the same. We set the deployment number of replicas to 1. We set the resource limits. This is important because this is what you end up paying for. We define the service and ingress and cross our fingers. Let's try to deploy this to AWS Fargate. Okay, excellent, that went smoothly. You can see that there is a single pod with our service running. Now let's see if it responds to the public URL. Okay, great, so everything is as we want it to be. Now let's try to update the number of replicas to 2. Okay, there we go. And now let's see if we're still in favor of the demo gods. Okay, deployment completed, and let's check the number of pods running and if the service is responding. So great, the number of pods has gone up to 2. And we can see the load balancer is distributing our calls between the 2 instances. Just to be complete, let's change it back to 1 and deploy the changes again. Okay, deployment finished. And Kubernetes reports only 1 pod running. So there we go. That was a simple demo showcasing how AWS EKS and Fargate work. I hope you found my talk interesting, and I would like to thank you all for attending. Goodbye.
Thank you, Zeljko, and we just have 2 speakers left for you for this conference. I know, time flies, doesn't it? And our penultimate speaker then is Meta. He's a developer advocate at Google, and he's focused on helping developers with Google Cloud. And I remember the last time I met Meta, what we talked about was the fact that we both actually lived in Greenwich in London. I don't live there anymore, but he's from London just like I am. Let's welcome Meta Atamel.
Hello everyone, my name is Meta Atamel. I am a developer advocate at Google, and today I want to talk to you about event-driven serverless architectures with Knative and Cloud Run. Now, before I start my talk, I want to let you know that I write about these topics on my blog at atamel.dev, and I tweet about them as well on my Twitter account, so feel free to follow me. And also the presentation is already on Speaker Deck, and here's the link, so feel free to get the presentation as well. I'm also going to be showing demos throughout the presentation, and they're all open source and on GitHub, and I'm going to share the links of that as we go through the presentation. Up until recently, we had to make a choice from the beginning, right? If we start a project and if we can use a serverless service from a cloud provider, like Google Cloud Functions or AWS Lambda or Azure Functions or something like that, great, we can do that, and that will give us a lot of velocity because we have a lot of things that's done for us, so we don't have to worry about the details of how to run that service, how to scale it and things like that. But at the same time, as soon as you run into a problem with the framework, you had to fall back to containers. And by problem, I mean things like the things that are supported. For example, if you want to run a certain language, like I don't know, like Rust or something else, maybe that's not supported in the framework that you want to use. So then you can use a serverless framework for that. So what people did is basically they went with serverless when they can, and they get the velocity with the serverless. But as soon as they cannot use it for whatever reason, then they will fall back to containers. And with containers, you get the flexibility, but then you kind of lose the velocity of serverless. So this was a really unfortunate choice that we had to make. But thankfully, the projects like Knative and Cloud Run, they try to kind of get rid of this choice so that you don't have to make this choice yourself. Knative, it's an open source project that was started by Google, but now it's fully open source and a number of companies are contributing to it as well. And the whole premise of Knative is to bring serverless to containers. So usually when we talk about serverless, we talk about serverless functions, but Knative tries to give you a way to deploy containers, but in a way that's serverless. And we'll talk about what this means as we go along. So that's Knative. It's open source. It runs everywhere there's Kubernetes, whether you run it on-prem or in the cloud. You can use it anywhere you want. But if you are running in Google Cloud, there's also two flavors of Knative called Cloud Run and Cloud Run on Anthos. These are managed version of Knative that Google provides. For example, Cloud Run, it's a fully managed service that implements the Knative API. So if you're already on Google Cloud, it's probably much easier to use Cloud Run instead of installing Knative yourself. And also there's something called Cloud Run on Anthos, which is a version of Cloud Run that runs on Google Kubernetes Engine. So if you want to stay in Kubernetes ecosystem, but you want to be in Google Cloud, you can use Cloud Run on Anthos as well. In today's talk, I'm mostly focusing on Knative because it's the open source version that runs everywhere. But most of the things that I'm going to talk about, they apply on Cloud Run as well. So you can run them easier with Cloud Run if you're in Google Cloud. But we'll focus on Knative in this talk. All right, so what is the Knative stack? Well, first of all, you have Kubernetes at the bottom layer. So that's the platform where everything runs. Then on top of that, you need to install a gateway. So Knative, it doesn't try to solve networking problems, right? So it doesn't try to figure out how do you get traffic from outside to your containers. Instead, it relies on a gateway like Istio or others that you need to install yourself and configure yourself. And then once you have Kubernetes and Istio installed, you can install the Knative components. There's two components of Knative. One is Knative serving, the other one is Knative eventing. I'm going to show you serving, but our focus will be more on the eventing side. And then at that point, you can use Knative if you want. But as I mentioned, if you're in a cloud provider like Google Cloud, you might want to look into Cloud Run or Cloud Run on Anthos. And other cloud providers, they have their own implementations as well. So you might want to check what else is built on top of Knative to use that instead, because it will be easier. Now, let's look at the first part of Knative, Knative serving, so that we understand what that does, and then we'll get into eventing. Knative serving, in a nutshell, it tries to give you a way to deploy containers so that it acts like a serverless framework. And what I mean by that is that, normally when you want to deploy a container on Kubernetes, you need to create a pod. Then you need to create a deployment, Kubernetes deployment. Then you need to create a Kubernetes service to expose the deployment to the outside world. Then if you are using Istio for traffic management, you need to create a gateway to enable the port. Then you need to create a virtual service to connect the gateway to your Kubernetes service. So there's a lot of things that you need to do to get a container up and running. And then you also need to worry about scaling the container up and down, stuff like that. So it's not that easy. Whereas in Knative serving, what you do is you create a Knative service and you point to your container and you say, okay, this is my container, it's deployed on Docker Hub or Google Container Registry. And then Knative serving takes care of the rest. It deploys your container in a pod, but you don't need to define the pod. So it does that for you automatically. Then it configures the traffic so that the traffic goes to your pod. Then it sets up automatic scaling. So your pod automatically scales down to 0 after 60 seconds, and then it will scale up to n that you define. Then on top of that, you get configuration and revision management. So every time you deploy your container, you get new revision. And with that new revision, you can, if you have multiple revisions, you can do traffic splitting, or you can roll back to a previous revision. So in a nutshell, it gives you a much easier way of deploying a container, getting the container auto-scaled, getting the container traffic managed, getting its traffic managed, and then you also have a really easy way of getting some kind of revisions and traffic splitting with those revisions. Now, the second part I want to mention is Knative eventing. And Knative eventing, all it tries to do is it tries to connect certain event sources to event consumers with certain delivery methods in the middle. So it tries to kind of connect different kinds of event sources to different kinds of event consumers with some kind of control in the middle that you can define how those events will flow in your system. These event consumers, they are usually Knative services, but they can be Kubernetes services as well. And the event sources and the event types, there's a lot of different choices here that we'll go through as well. And you also have a lot of choice on how those events get delivered to your services. Now, the terminology of Knative eventing is that, first of all, you have cloud events. So this is the format of the events that we'll talk about. Then you have event sources. So who's actually creating the event, or where are we pulling events from? These are the event sources. Then once the events get into your cluster, they go to somewhere called broker, which is, it's a place that gets the events within your namespace. And then from the broker, you want to send the messages to your services, but you define that through what's called triggers. And then finally, you have services receiving these messages, Knative or Kubernetes services. We'll go through these one by one and look at them in more detail. Finally, there's also channels and subscriptions, but we don't really need to worry about this too much. There are things that are created under the covers, but once in a while, you might need to look at them. So that's why I will mention them briefly here. Now, first of all, as I mentioned, the format of the events is cloud events. And cloud events, it's an open source eventing format from CNCF. So you can check it out in more detail at cloudevents.io. And these cloud events, they basically define a kind of high-level event definition, right? For example, when you look at cloud event here, it has a spec version, which is the version of cloud event. 1.0 is the version. Then the event type and the event source. These are the things that you need in any kind of eventing system. Then you have the typical things like the ID and the time of the event. And finally, the data of the event is the thing that holds the actual payload. So for example, in here, we are listening FTP, GitHub, Google Cloud Storage kind of events. They all come in, they all get converted into cloud events, and the data field will have the actual event that you're interested in. And then when the broker gets the event, he will get it in that format, right? And I should also mention that Cloud Events has SDKs to actually read and write events. So if you want to use them, you would start with SDKs. And Google Cloud also has libraries to parse this data field, right? So if you're reading, say, Google Cloud Storage event, you would use this Google Events libraries to parse that event as well. So that's the format of the events, but what kind of events we can listen? Well, basically, there's a lot of different kinds of events. So you can listen AWS events, You can listen Google Cloud PubSub events, Google Cloud Storage events. This is not the full list. You can check this link for the full list, but there's a lot of different event sources that you can install and list and pull messages in to your cluster. You can also write your own event sources. So if you have something custom that you want to read from, you can write your own custom event source. Now, as I mentioned, Google Cloud has different kinds of event sources to read Google Cloud sources into Knative. These are all defined in a project called Knative GCP project. And in this project, there's a number of event sources. There's, for example, Google Cloud PubSub source. That's for reading PubSub messages into Knative cluster. There's Google Cloud Storage source to read Google Cloud Storage events into your cluster. There's Scheduler source to kind of create Google Cloud schedules that run on a certain schedule and call certain services. So you can set that up with Google Cloud Scheduler source. So these are very useful, basically, if you're in Google Cloud and if you want to read Google Cloud sources, you can install them and then they let you read these events in an easier way. And that's what I'm going to use in my demo that I'm going to show you. Now, this demo that I want to show you, it's a BigQuery processing pipeline. And what I wanted to do is that, I'm based in London and we started having lockdown in mid-March. We all started working from home. And at the time, COVID was a new thing. So I was checking the number of cases in London every day, at 4 or 5 p.m. I would check out and see what were the numbers for the day. So after like a week or two, I thought to myself, instead of me checking these cases by myself, why don't I build a pipeline that would check these numbers for me, and then it would send me an email every day at a certain time with the latest numbers, and maybe it will send me a chart as well. So I basically wanted an easy way to see the numbers for every day without me having to check for it. So that's when I started building this pipeline. So the way I built this pipeline is kind of like this. First, I said to myself, okay, how can I get this data? Where can I get this data? And in Google Cloud, there's something called BigQuery. BigQuery is a data warehousing solution. And the good thing about BigQuery is that it comes with lots of public data sets. And one of those, not one, but a few of those data sets is related to COVID. So what I did is first I built a service called Query Runner. This is a Knative service that will go to BigQuery and it will ask BigQuery using the COVID data set, what are the number of cases for this country in the last month or so, right? So it will query that, it will get that data, and it will save it to a temporary table. You can create temporary tables in BigQuery, so I will ask to BigQuery and save it to a temporary table. So that was my service number one, but I wanted this service to be triggered on a schedule, so I used Google Cloud Scheduler to trigger that service once a day at 4 p.m. for United Kingdom, for example. Now, once I make this query and save it to a table, I send a custom event. So I reply back to broker and say, okay, I run a query. So I just reply back with a custom event that goes to another service called Chart Creator. It's a Python service that will read this table and it will create a chart from it using Matplotlib library, right? So it will read this table, create a chart, and it will save it to a Google Cloud Storage bucket. And then I set this bucket so that when an image is saved here, a chart is saved here, it will call another service called Notifier, which is another Python service that will use SendGrid to send me an email. And it will say, okay, there's a new chart created in the storage. Here's the link to go and take a look, right? So the good thing here is that it's event driven. So the scheduler triggers the event and then that triggers the whole chain. But none of these services, they know each other. The query runner just runs the query, then sends a message back to broker, and then that goes to chart creator. All it does is, it kind of just reads the table and creates the chart, so it doesn't know that there's a query runner. Similarly, Notifier, all it cares is that there's a new chart in the bucket, so it gets a notification of that. So the whole thing is loosely coupled, event-driven, and in the end I get an email at the end of the day. So let's actually look at this in detail. So first, let me show you the code, not the code, but the configuration at least. And the code is on GitHub, by the way. So if you look at BigQuery, first what I need to do is I need to create scheduler sources. So in Knative, there's, as I mentioned, in Knative GCP project, there's different sources. So in this one, I'm saying I'm going to use Cloud Scheduler source, and it will be triggered every day at 4 p.m. and it will send a message to the broker with this data, and the data is United Kingdom. And my broker will pass this to my query runner, and query runner will get this United Kingdom data, and it will say, okay, I'll ask BigQuery what's the numbers for United Kingdom is. So that's my scheduler source. Then the storage source is my charts. Once I say my charts, after the chart creator says the charts, it will send a message to the broker, and the broker will get the notification that there's a new chart in this bucket, right? So these are a couple of my sources. If you look at the query runner, I mean, the code itself, we don't have time to go through it, but basically it gets the cloud event. So this is the event reader that I created. It gets the cloud event, then it extracts the country from it, then it runs a BigQuery job, and then once it does that, it sends a message back to the broker that I run this job, and there's a new table. But the interesting thing is to look at the Knative service. So the Knative service is the query runner that just points to the query runner container, and the trigger, it triggers on filtering on job scheduler. So it only looks for cloud scheduler events. So only triggers on the cloud scheduler events, right? So that's query runner. Then after that, it goes to chart creator. And chart creator, we don't have to look at the Python code, but if you look at the trigger, the chart creator will only look at the query completed custom message, right? So this is a custom message that the query runner will emit, and then it will go to this chart creator. And then similarly, notifier will only trigger on object finalize. So whenever there's a storage bucket update, it basically will emit this storage object finalize event, and this is what the notifier will get, right? So let's actually set this up and see if it works. So let me get out of here and go to eventing, processing pipelines, BigQuery. Now, I think I can get rid of this. Okay, so let's make this a little bit bigger. All right, so let's first create the scheduler source UK. So this creates the cloud scheduler source for UK. And then let's also create the storage source so that when we say the charts, we get those events as well. And then we will get into query runner, and then we'll create the Knative service and then the Knative trigger for that. And then let's do the same for chart creator. And then let's do the same for notifier. All right. So if everything goes well, we can look at our services. So you can see that we have 3 services that's been created. And then we can look at the triggers that's been created. And the triggers, they are being initialized. They will talk to the default broker. And I already have a broker injected into my namespace. So the default broker is there. And let's also look at cloud scheduler source. So this is the thing that will trigger the events. And then cloud storage source is the thing that will trigger storage events. So everything seems to be set up. Now we can wait till 4 p.m. for it to be triggered, but we can also manually trigger this event. So if I do gcloud scheduler jobs list, we can see that there's a job that's been created that will trigger at 4 p.m. But let's actually trigger this ourselves. So if I do jobs run and then pass in the ID. This should trigger the job now, and then now the whole event chain is being initialized. So if everything goes well, this will go to the query runner. Query runner will actually run the query, and if you actually look at the logs, you can see that we have the services running. So let's just take a look at the logs of query runner. Oh, sorry. Yeah, the query run is actually terminating because they scaled down, right? So if I look at pods again, you can see that they scaled down. So I couldn't see the logs, but I think the whole thing ran. So if I look at my email, you can see that I got an email, a new chart from BigQuery pipeline, and if I open it, I have a link to a chart. A new chart is available. Let's just take a look. You can see that I can see the COVID cases in United Kingdom. That I get the chart, from the beginning of March till today. So that's it. Hopefully this was useful to you. As I mentioned, the presentation is already on speaker deck, so feel free to get it there. My Knative tutorial on GitHub, it has many more samples than I showed you today. Hopefully the samples that I showed you, it was useful and you have an idea on how Knative works. Also, as I mentioned, Knative, if you want to run Knative on Google Cloud, you probably want to use Cloud Run. And I also have a Cloud Run tutorial on GitHub for that as well, so feel free to check it out. Thanks for listening, and if you have any questions, feel free to reach out to me on Twitter. I'll be happy to answer it. Thanks very much.
Thank you, Meta. And now, our final speaker of the 10th Shift Remote it's been writing code rather since they first touched a Commodore 64 in the mid-80s. He's inspiring builders to unlock the value of the AWS cloud using his what he calls secret blend of passion, enthusiasm, customer advocacy, creativity, and curiosity. He's the host of the official AWS FR podcast and the AWS video channel in French. Let's welcome Sébastien Stormark.
Hello, good evening, good morning, wherever you are. Thank you for watching this talk. In this talk, I'm going to talk about how you can simplify your mobile or web application by using a cloud-based serverless resource. So that's a lot of buzzword in one single title. Cloud-based serverless resource. I'm going to explain all of that. So stay tuned, attach your seatbelt, and let's start. My name is Sebastian. I'm developer advocate for AWS in Europe. I was in the Shift conference last year in Splits, and I really regret I cannot be there in person this year, but I have good hope that the world will soon reopen and that I will be able to travel again next year to talk to you, to meet you in person, to answer your question and to listen to your stories about what you are building on AWS. So, what's the typical day in a developer life? Typical day in a developer life, it's your project manager knocking on your shoulder saying, hey, we need to have that new application super soon because you know competition is there already. And by the way, we don't have budget, so you will be alone. Please do not expense too much on IT resource because you will be the only one to manage and to operate that without budget. And previously, in a previous life, maybe you want to hang yourself there saying, okay, or stop saying, I don't want to work in IT anymore. That's a good time to be a bartender on a beach somewhere with sun. But today with the cloud, you say, why not? I can do that. I can use a cloud-based serverless backend to meet this type of specification. If you look at the Stack Overflow developer survey results, I know this one is 2 years ago because Stack Overflow is not querying on cloud anymore. But this one from 2018 says serverless 75% is the most loved technologies or wanted technology for by developer, and the cloud, the AWS cloud specifically, 68%. So what is serverless? Serverless, of course, doesn't mean empty data center, empty racks, and no server. There is no magic there. You still need server to run your code, to store your files. But serverless means someone else is managing this server, so you don't have to manage any type of infrastructure. There is no added value for you to provision Linux or Windows Server, to install Linux, to patch Linux, to monitor the CPU, the memory, to monitor the storage, to react to production incidents, restart virtual machine. This doesn't make your application better than the one from the competition. This doesn't help you to build a better application. To the opposite, it drags times away from you to work on more added value tasks. So let's have someone else manage the server for you, and that's a serverless. Serverless solution also scales with usage. So if you have 1 user per day or 1 million users per day, you have nothing to change because it's not your responsibility anymore. So there is no more scaling, load balancing. All of that is hidden, and the cloud provider, AWS, will do that for you. Serverless solution will also benefit from the high availability built into the system. So if you are using AWS cloud systems, we design our system to be highly available and resistant to failure. And the best part of serverless is that you are going to pay for the value. It means if you are not using it, you are not going to pay for it. Hey, here I can hear some people saying, yeah, but it was like that with virtual machines as well. If I shut down the virtual machine, I'm stop paying for it. Yes, but if you have a virtual machine running, you pay for the virtual machine, even if there is no user. With serverless, it's not the case. If there is no user, you're not paying for it. So it's not exactly like a virtual machine. For a cloud function or an API or a database, if there is no request made to these, then you are not going to pay for these. So serverless is across the stack. It's not only for compute. Typically serverless, people think about cloud functions like AWS Lambda, but it's not only for cloud function. If you think about API, gateway, or developer tools such as the environment where you can build, test, and deploy your code, there is no need to have a virtual machine running and software installed on that you need to maintain just for your build environment. I love Jenkins, but maybe there is a different way to do that. And it's the same for database as well, with Aurora, with time series database, with DynamoDB, for example. You can also store your data without having you to think about provisioning server, provisioning storage, or doing backup of your storage. But when developer wants to adopt the cloud, what are the obstacles they are facing? First, we have a lot of services. We have more than 170 services today in all possible categories, being IoT, analytics, data lake, migration, mobile, core, or anything else. And that's a lot of service to learn, and finding the right service to use is not always an easy job. It's also a challenge to write the basic configuration code that is required to work with most of these services. So how are you going to configure this service out of the box? And this is where Amplify can help. So Amplify is an open source framework that we designed for you to help you to provision and to use these services. It's an opinionated framework. It means that we do apply some default there, the default that makes sense for more than 80-90% of the developer. If you want to change this default, of course it's possible, it's up to you, but we try to drive you into the best practices that we observe from a customer. The last 10 years they are building web and mobile application on the AWS cloud. And Amplified, it's made of two parts. First, it's a command line. So it's a tool that you can use from your Windows, Linux, or Mac machine. It's called Amplify, and it helps you to provision serverless resource in the cloud. So by asking you very few questions, it will create a configuration file and create the service and configure the service for you in the cloud. Amplified is structured around categories, so like there is an authentication category, an API category, a storage category to create services, and depending on the use case of your application. And once you are done, you just type Amplify push, it will generate code and execute that code for you in the cloud. For those of you that know AWS CloudFormation, Amplify is just with double quotes, generating CloudFormation templates and executing these templates migrates into the cloud for you. So that's the first part of Amplify, the command line. The second part of Amplify, it's a set of open source libraries. So if you develop for web application, we have open source libraries for Ionic, Vue, Angular, and React framework. We also have plain JavaScript. If you prefer to have JavaScript, no problem, we can do that for you. And for mobile application developer, we do integrate with Android, with Java and Kotlin, and iOS with Objective-C or Swift, but most of our framework is in Swift. So let's do that, and let's enrich an iOS application. Let's see how it works from a developer point of view. I choose to make the demo with iOS because this is what I'm working on these days, but it's not mandatory for you to use on iOS. It can be Android, and if you're a web application developer, the same concept applies. So you will find relations with what you're doing inside your React application, for example, and what I will show with iOS. So don't zap, don't lose, don't disconnect if you're a web application developer. This is still valid for a web as well. So the first step is always to initialize Amplify. It will ask you a few questions and create an S3 bucket for you where it can provision files on your behalf. It takes 1 or 2 minutes. It's not very sexy. I'll skip that part of the demo. But the first step you probably want to do in your application is to add user authentication. So let's see how it works. Using Amplify, I can just type Amplify add auth. Amplify will ask me a couple of questions, and with Amplify push, it will create infrastructure for me in the cloud to handle user authentication. On the client side, what does it mean? I need to add the authentication plugin with just Amplify add and the name of the plugin. The syntax is different if you're doing it for the web or for Android, but the concept is the same. Once you do that, it creates for you an AWS Cognito user pool. So once you type Amplify push, it creates for you in the cloud a Cognito user pool. So Cognito, it's a serverless service to manage user authentication. It allows to store accounts such as username, email, password. It provides API for sign up, sign in, reset password, and many other flows for the user. It does support multi-factor authentication with SMS or one-time password. It also supports identity federation, more about that in a minute. So a user pool, it's like the database where we are going to store your user profile, and then you can create a custom user interface in your application to interact with that user pool. Cognito, the code is just sign in, amplify.auth.signin with username and password, and then you provide a callback that will be called a bit later in case of success or error. The other option, instead of collecting the username and password inside your application, is to delegate authentication to the web interface of Cognito. So Cognito has also a customer-facing page where a customer can authenticate by entering the username password. It has a screen for sign up, sign in, reset password flows, and it can implement identity federation. So Cognito can be the client for login with Facebook, login with Google, login with Amazon, or anything that supports OpenID Connect. And because you configure that on the server side, it's between Cognito server and Google, Facebook, Amazon, there is no change of the code that you need to write on the client side. So that's a very easy way for you to add for identity federation on the server side using Cognito user pool. The only difference at code level is instead of calling signing with a username and password, you need to call signing with web user interface, and that's it. Amplify will redirect your customer to the Cognito web interface with 0 lines of code. You can add a federation with Facebook, Google, Apple, or any other without adding a single line of code inside your application. So let's see in practice how it works. I'm switching here to my terminal. I'm in a demo project, and the first thing I'm going to do is to type Amplify add auth. It will ask me how I want to authenticate my user, and here I want with social provider, so the web interface with identity federation. I need to give the domain name for Cognito and the redirect URI, because the authentication will happen on the web. Cognito needs to know where to redirect the user at the end of the authentication. So for a native app, I create a custom URI and configure my app to be launched when that URI is called. Next step is to create Amplify push, to type Amplify push. That will create the CloudFormation file and create the Cognito user pool in the cloud. In reality, it takes 1 to 2 minutes to complete that step. So I accelerate the video here so that you and me, we don't have to wait. At the end, we receive the web endpoint where user can authenticate on Cognito, and I also receive a test endpoint. So let's switch to Xcode and my iOS application. Here I have two methods, signing with username and password and signing with the hosted user interface. And I will show you how the two are working. In my user interface, I have a signing button, and that signing button just when you click on that, it's called authenticated with the web user interface. So if I try that, you can see the signing button. You click on sign in, and the user is redirected to the Cognito web user interface where I have configured login with Facebook, but here I choose to connect with a username and password that I already created in the Cognito user pool, and after that I'm redirected to my app and the rest of the app can work. I can sign out, continue, redirected to Cognito, and I'm signed out of the web user interface. If I want to create a custom login page, I switch to another view in my code, and here it's a page of my app that collects the username and password, and that calls the other Amplify API, sign in with username password, and you see that the user experience is roughly the same. So super easy to integrate Cognito user pool from your mobile or web application using Amplify. The second step is to add an API. So what type of API can we have in Amplify? We can have either REST API or GraphQL API. For this demo, I chose GraphQL. GraphQL is a query language for API. It all starts with a type. You define the type of the data that you want to work on. So that's a big difference with REST. So in REST, there is no type. In GraphQL, there is a type. It's strongly type description. And GraphQL defines operation as well. So query operation to query your API, mutation for the create, update, delete part of your API, and something that does not exist with REST. On GraphQL, you have also the concept of a subscription. So subscription is really listening to change that are coming from the server side so that you can reflect change on the server into the customer user interface. GraphQL has been created by Facebook, and that's what they are using inside their mobile and web interface, for example. So how does that work? If you choose GraphQL at runtime, you need a GraphQL server, and we have that, a serverless service. It's called AppSync on AWS. And AppSync is the service that will receive the queries, the subscription, the mutation order coming from your client. It will analyze that and fetch the data from multiple data sources. Might be from a REST interface, might be from DynamoDB, from a Lambda function. This is made through what GraphQL calls resolver. And all these resolvers are going to be called in parallel to collect all the data that we need to fulfill your query, and AppSync will return a JSON document with the data returned by the resolver. From the Amplify point of view, of course, you do not need to create the AppSync server. We are going to do that for you. So you just type Amplify add API, you answer a couple of questions, and then you Amplify push. The questions are very simple. Do you want to implement a REST API or GraphQL API? How do you want to authenticate the user? And do you have a schema already for that API? So the schema I'm going to use for my mobile application, it's a landmark data. Remember the application that you saw? It allows you to track landmarks. And the landmarks are just an ID and name. You notice the exclamation mark. It means that these fields are mandatory. The others are optional, like a category, city, state, it's a string. You have is feature, is favorite, it's Boolean, and so on and so on. That's my schema for the GraphQL API. You can annotate your schema. Developers are quite familiar with the concept of annotation. In GraphQL world, we call that a transformer, and here are two examples of transformer that we do support. The model transformer tells Amplify to generate a database, so it makes your data persistent. The auth transformer defines rules that are going to be applied by Amplify and AppSync to define who can access your data. And here I want only user authenticated with my Cognito user pool, and these data are private. I only the user that creates that landmark data can see, read, and update the landmark data. Because GraphQL is strongly typed, we can also generate code for you automatically. So with Amplify code and models, we are going to generate the model based on your GraphQL type definition. And we do generate models for Java, Kotlin, Swift for iOS, and of course JavaScript for the web framework. So it means that you, as a developer, you do not need to write boilerplate code to represent your data. We are going to do that automatically. Here in Swift iOS, I'm just calling Amplify API query, and I query for list of landmark data object. Once again, landmark data objects have been created for me automatically. It's exactly the same if you want to use Kotlin Java or JavaScript for your web application. Then you wait for the callback to be called and you inspect the callback value. If it is a success, you update the user interface. On mobile, Android and iOS, it has to be done from the main user interface thread, hence my dispatch queue main async, and there is a similar mechanism on Android. On JavaScript, you don't care too much about threading, so you can directly update your user interface from the callback there. On the backend, what we are going to create, it's an AppSync and a DynamoDB table to store my data. So DynamoDB is a managed serverless NoSQL database, and AppSync has mostly three parts. One part is the data source. It's like the connector that allows to connect to a specific data source. So Amplify will create a DynamoDB data source for me. On the front part, it will create all the schema for me. So based on my model definition, on the types, it will create the mutations, the subscription, and the query operation. So list landmark, get landmark, create landmark, update landmark, delete landmark, subscribe to landmark, change, and so on and so on. So all that boilerplate code is generated by Amplify automatically. In between, the resolver, it's the link between the schema and the data source. So it's the piece of code that tells, okay, for list landmark, we need to go to the data source landmark and we need to send that or that type of queries to DynamoDB. And this is how to extract the JSON out of DynamoDB to return the JSON back to the client code. So the resolver are also generated automatically by Amplify. The resolver are also important for security because this is where we are going to filter based on the owner field. So this is where we are going to implement the fact that only the owner can read or update a specific piece of data. So all of that is generated by Amplify, and you can use it as I show you in the code from your mobile application. Next and last step is to add file storage. File storage in my landmark application would be to store the picture of the landmarks, for example. So typically on AWS, I'm going to use Amazon S3, but I don't want to write boilerplate code for that. So Amplify as storage will create an S3 bucket for me and will secure that bucket for me automatically. In the library, Amplify is providing me with high-level methods such as download data, upload data, with progress listener, result listener, so that my code can receive notification about the status of the download or the upload. It will manage the security of the bucket for me and the access to the bucket for me as well. On the server side, the component is creating for me, it's an Amazon S3 bucket to store the data. If you have a web app, you most probably want to deploy that web app and host that web app. In the old days, last century, you would probably start a couple of virtual machines and install Apache or Nginx by yourself. But what is the best place than Amazon S3 to host your web app? S3 has unlimited storage, very good high availability, and it talks HTTPS by default, and your customer browsers is also talking HTTPS. So you can configure Amazon S3 to be a web server, and that's what Amplify Add Hosting does. Amplify Add Hosting, Amplify Publish It asks you if you want to work in dev or prod, the name of the bucket and the name of the index document, and that's it. It creates for you a bucket, configure that bucket to be a web server, and will deploy your HTML, JavaScript, static image on the server side. So for web application, once again, it doesn't apply to a mobile application, but for web application, that's a very convenient way for you to host your static content and your HTML and JavaScript page. If you answer prod instead of dev, then we will put a CDN in front of it. CDN in the AWS world, it's Amazon CloudFront. It's a CDN with hundreds of locations around the world where we can cache the content close to your customer to reduce the latency it takes for your customer to access your content. So customer will be redirected to the closest cache, close to where they are. And if the file is not there, or if it is expired, then CloudFront will make a request to the origin, to the source on S3, and then will cache the content for other customer in the same geographic area. When talking with developer, many of us told us that one of the requirements of the application is to also operate offline. You know, you go through a tunnel, you lose connection, but you want your customer to continue to use the application during that time. And for that use case, we implement Amplify Data Store as of last year. So Data Store, it's a multi-platform on-device storage solution. As a developer, you just interact with the local data store, and Amplify Data Store is going to synchronize your local data with the GraphQL backend that you just created. So there is a synchronization engine there that takes care of conflict resolution. It has a default policy for conflict resolution, but of course you can implement your own policy if you want to resolve conflict the way you want. So the way it works is you as a developer, you just interact with the local data store. So on the web, we are using IndexedDB to store your data, and the Amplify library provides you with CRUD operation, create, read, update, delete operation on this local data store. On Android and iOS, we are using SQLite for that. Once you store your data, we have a synchronization engine that will send the queries and the mutation back to the backend over GraphQL, and it will use the subscription mechanism I mentioned before to listen to change that happen on the backend to synchronize back your local data. It uses a second DynamoDB table to keep track of the change and the versioning of the records, and that's how we can handle conflict in an optimistic way most of the time. Otherwise, I told you, you can have a conflict resolution either on the server side, either on the client side. A couple of other black belt tips for Amplify. Amplify does follow your Git workflow. So if you are working with multiple branch, you can type Amplify checkout and the name of your branch to have multiple environment on the backend. So you might have a prod, dev, test feature 1, test feature 2 structure on the backend. So we are going to duplicate the DynamoDB, the AppSync, the storage, and all the service I talk about. So all these environment will be duplicated one per branch. Once you merge the branch after a pull request, the temporary environments are going to be deleted automatically. So it nicely integrates with the Git workflow. And once again, for web application, we have also a CI/CD capability, so continuous integration, and continuous deployment. So you can hook it up your favorite source repository. It might be GitLab, GitHub, Bitbucket, or of course AWS Code Commit. And every change detected on these will trigger a build in a serverless environment. You just give us a build file, so how to build your application. If it is, I don't know, static website with React, Hugo, Jekyll, and these type of things. And that's a YAML file that you include inside your project. So we are going to build your project and automatically deploy your project. If you create a pull request, it will automatically deploy in a second environment where you can preview the change before accepting to merge or not the pull request, and to delete the temporary environment after you merge your pull request. So it's super flexible, super easy to set up, no virtual machines, to create your continuous integration and continuous deployment environment using Amplify and Amplify console. And it also comes with a nice user interface where you can see the different stage. It takes a screenshot of your web application so you can see if your web application is correctly deployed or not. And of course you can follow and receive the logs for all that automatically. Last thing I want to talk about is a new category that we added 1 year ago. It's called prediction, and prediction, it's like an artificial intelligence machine learning category that gives you super easy access to many machine learning service that we are providing on AWS. So using the prediction category, you can very easily as you can call an API or implement storage, as I show you in this talk, you can call a machine learning service such as transcribe, poly, or prediction. So these services allows you to translate text from one language to the other, or to transcribe if you have the sound file of a recording. It can generate text, the corresponding text. You can analyze the text to detect sentiment. Is it positive? Is it negative? What this text is talking about. You can recognize label inside an image, or recognize object inside an image for content moderation, for example. What else can you do? You can also convert text to speech, or generate a voice in multiple language, female voice or male voice, depending on your preference. And all these are available with just one line of code inside the Amplify application. So what did I show you in this talk? I show you how to use the Amplify framework to include cloud-based serverless resource inside your application. I first show you how to add user authentication using Amazon Cognito with signing, sign up, and identity federation flows. Then I show you how to add API, GraphQL API inside your application. We can do the same with REST if you prefer to work with REST. And this was using AWS AppSync and DynamoDB. Then I show you how to create storage with Amazon S3. If you want to explore all these steps by yourself, you can follow my workshops on Amplify iOS workshops. go-aws.com, step-by-step instruction to create the landmark application that I just showed you inside this talk. And there is an Android tutorial as well. There is an iOS tutorial. Just Google Amplify Android, and my colleague Nader is creating tons of content for React or for Next.js, for example, if you prefer server-side rendering for your Amplify application as well. So tons of resources available for you. Search using your favorite search engine, you will find them quite easily. Just to finish, this is the architecture of the application I show you today. You have the client application using Amplify libraries, using serverless backend in the cloud, Cognito to manage user, AppSync for GraphQL API, DynamoDB to store the data, and S3, and S3 to store your picture. All that managed just from your command line Amplify and the Amplify libraries. So now it's your turn. You have to build something, using Amplify, a web or mobile application, and tell us what you think. Share your feedback through social media, or just open issues on GitHub, for example, for Amplify. You can find me on social media, on Twitter, Sebsto, S-E-B-S-T-O. I'm also quite present on Twitch and YouTube, but this is mostly in French. And there is a code sample on my GitHub repository on Sebsto, S-E-B-S-T-O. Thank you for having watched that talk. Please send me your feedback, ask your question, don't be shy, engage the conversation. I'm not here with you physically today, but we can talk over LinkedIn and Twitter, Sebsto, S-E-B-S-T-O. I will be more than happy to talk with you and to answer your question. See you really soon. Bye.
Thank you, Seb Stormak. And with that, we have reached the end of the 10th Shift Remote. Thank you so much to our incredible audience, you, for listening in and being here. If you've liked it, if you've had a good time, let us know there in the chat. Remember, on the 7th and the 8th of December is our Shift Money in-person conference in Zagreb, Croatia. Don't forget to grab a ticket online and register your interest. Let everyone know online, keep using that hashtag Shift Remote. But that's it from us here at Shift. We want to say a huge thank you once again to our supporters and sponsors at Microsoft, Infobip, Raiffeisen Bank, Autodesk, Microblink, Barrage, Azure idea, ICT, Japania, Venture pseudocode, 5 Ars Futura, Nanobit, Infinium Q, 9 Dots, Get by Bus, Aspira, Code Anywhere and Pluggy. Without all of you, this would not have been possible. So thank you so much. And we'll see you again at the next Shift